Hello, and welcome. Tonight we are going through 67 levels of logical paradoxes, which will either guide you to sleep or might keep you awake. Either way, it's way better than doom scrolling at 2 a.m. If this feels like your corner of the internet, consider the YouTube rituals. Let me start with something simple. You haven't subscribed to this channel, but I believe you did. Take a moment with that sentence. Something feels off about it, doesn't it? Here's what's strange. Both parts of the sentence could actually be true as facts. Maybe you really haven't clicked the subscribe button, and maybe I really do believe you did. There's no logical contradiction in those facts existing together. So why does it sound so broken when I say it? The problem is this. When you say something out loud, you're showing that you believe it. That's what making a statement does. If I say, "The sky is blue," I'm not just making sounds, I'm showing you that I believe the sky is blue. So when I say, "You haven't subscribed," I'm showing you that I believe you haven't subscribed. But then I immediately say, "But I believe you did." I just showed you I believe one thing, then claimed I believe the opposite. It's like opening a door while saying you're closing it. The action contradicts itself. Here's the classic form of this paradox. Imagine someone says, "It's raining outside, but I don't believe it's raining." That sounds completely broken. Yet someone else could say about that person, "It's raining, but they don't believe it's raining." That sentence is perfectly fine. Same facts, same reality, but one can be said and the other cannot. This is Moore's paradox, named for philosopher G.E. Moore. It shows that truth and belief are not the same thing. Speaking isn't just about stating facts, it's about revealing what you believe. And some statements defeat themselves the moment you say them. This paradox helped shape modern logic and artificial intelligence. When we program computers to understand language, we have to teach them the difference between what's true and what can be sincerely asserted. Moore's paradox revealed that human communication has hidden rules we didn't even know existed, rules that now help machines understand how we actually talk. So, if that sentence felt broken to you, the subscribe button is right there. Let's find out which part of my statement was true. Imagine a small, quiet village. In this village, there's a barber. This barber has a very specific rule that defines his entire profession. He shaves all those men, and only those men, who do not shave themselves. It's a simple, clear rule that seems perfectly reasonable. All the men who shave themselves, the barber doesn't shave them. They take care of their own grooming. But all the men who don't shave themselves, the barber shaves them. That's his job. That's what he does. For years, this system works perfectly well. Everyone in the village knows the rule, and it causes no problems whatsoever. But now, let me ask you a question. Does the barber shave himself? Think about it carefully. If the barber does shave himself, then he's one of those men who shaves himself. And according to the rule, the barber only shaves men who do not shave themselves. So if he shaves himself, he violates his own rule. He shouldn't be shaving himself. Okay, so maybe he doesn't shave himself. If the barber doesn't shave himself, then he's one of those men who doesn't shave himself. And according to the rule, the barber shaves all men who don't shave themselves. So the barber must shave himself. Do you see the problem? He can neither shave himself nor not shave himself without creating a logical contradiction. The very rule that defines his job makes his job logically impossible. This is the barber paradox, formulated by the philosopher Bertrand Russell. It reveals how self-reference can create logical impossibilities that seem perfectly reasonable until you examine them closely. This paradox helped expose problems in early set theory and changed the foundations of mathematics. Level 3. Achilles and the tortoise. The great warrior Achilles, legendary for his speed, decides to race a tortoise. Because Achilles can run much faster than the tortoise, he sportingly gives the tortoise a head start. Let's say the tortoise begins 100 meters ahead. The race begins. Achilles runs swiftly toward the point where the tortoise started, but by the time Achilles reaches that 100-meter mark, the tortoise has moved forward a bit, perhaps 10 meters further. No problem, Achilles thinks. He runs to cover those 10 meters. But when he reaches that new point, the tortoise has moved ahead again. Maybe just 1 meter this time, but still ahead. Achilles covers that meter. The tortoise has moved 10 centimeters. Achilles covers those 10 centimeters. The tortoise has moved 1 centimeter. This pattern continues endlessly. Every single time Achilles reaches the point where the tortoise was, the tortoise has moved a little bit further ahead. The ancient Greek philosopher Zeno observed this and made a startling claim. Achilles must complete an infinite number of these catching up tasks. First, reach the 100-meter mark, then reach the 10-meter mark beyond that, then the 1-meter mark, then the 10-centimeter mark, on and on, infinitely. Since there are infinite tasks to complete, and completing infinite tasks would take infinite time, Zeno concluded that Achilles can never actually overtake the tortoise. The race can never be completed. Motion itself, Zeno argued, is impossible. It's an illusion. Yet we know from everyday experience that fast runners do overtake slow ones. We know motion happens. So what's wrong with the logic? This paradox troubled the greatest minds for over 2,000 years. It eventually led to the development of calculus and our modern understanding of infinite series. The resolution involves understanding that an infinite number of tasks can take a finite amount of time, if each task takes progressively less time. But Zeno's paradox still reveals how deeply strange infinity really is. There's an ancient ship, a beautiful wooden vessel that belongs to Theseus. This ship has been sailing for many years, and like all wooden ships, it requires constant maintenance. Over time, the planks begin to rot from exposure to salt water and weather. When a plank rots, Theseus replaces it with a new plank of the same size and shape. One plank gets replaced. The ship looks the same, functions the same, and Theseus considers it the same ship. A few months later, another needs replacing, then another, and another. This continues year after year. Eventually, after many years of careful maintenance, every single original plank has been replaced. Not one piece of the original physical material remains. It's all new wood. Yet the ship has maintained its form throughout this entire process. There was never a single moment when you could point and say, now it's a different ship. So here's the question. Is this still the ship of Theseus? Or is it a completely different ship? Most people's intuition says it's still the same ship. After all, it was gradually repaired and maintained its continuity throughout. But now imagine something else. Imagine that someone had been collecting all those old rotted planks that were removed. They took them, repaired them, and reassembled them into a ship using the exact same configuration as the original. Now there are two ships. One has physical continuity through gradual replacement. The other contains all the original materials. Which one is the real ship of Theseus? Which one has the true identity of the original? And here's an even deeper question. If the continuously repaired ship is the real one, at what exact point during the replacement process did the original ship cease to exist and a new ship come into being? After the first plank was replaced? After half the planks? Where do you draw the line? This paradox, recorded by the ancient philosopher Plutarch, questions the very nature of identity. What makes something itself?
Is identity about physical materials or about continuity and form? This same question applies to you. Your cells are constantly dying and being replaced. Are you the same person you were 7 years ago when every cell in your body was different?
Level 5. The unexpected hanging paradox. A judge sentences a prisoner to death. The prisoner will be hanged at noon on one weekday in the following week, Monday through Friday. But there's a special condition. The execution will be a surprise. The prisoner will not know which day he'll be hanged until the executioner knocks on his cell door at noon that day. The prisoner returns to his cell and begins to think about this sentence. He's a logical person, and he starts to reason through the possibilities. The hanging cannot be on Friday, he thinks, because if I'm still alive when Thursday night arrives, I'll know with certainty that the hanging must be on Friday. It's the last possible day. But if I know it's coming on Friday, then it won't be a surprise. That contradicts the judge's statement. So Friday is logically impossible. He continues his reasoning. Now that I've eliminated Friday, Thursday becomes the last possible day. But if I'm still alive Wednesday night, I'll know the hanging must be Thursday. Again, it wouldn't be a surprise. So Thursday is also impossible. The prisoner applies this same logic backwards through the week. Wednesday is impossible for the same reason. If I survive Tuesday night, I'll know it's Wednesday. Tuesday is impossible, I'd know by Monday night. And Monday is impossible because I'd know right now that it must be Monday, since all other days are eliminated. The prisoner concludes, with seemingly airtight logic, that the surprise hanging is impossible. The judge's sentence contains a logical contradiction. He relaxes, confident he won't be hanged at all. Wednesday arrives. At noon, the executioner knocks on his door. The prisoner is genuinely, completely surprised. The hanging occurs exactly as the judge predicted. But how is this possible? The prisoner's logic seemed perfect. Each step followed validly from the previous one, yet his conclusion was completely wrong. Where did the reasoning fail? This paradox has puzzled logicians for decades. It reveals something deep about knowledge, prediction, and self-reference. The prisoner's logic defeats itself. By concluding the hanging is impossible, he makes himself able to be surprised. The paradox shows that some forms of logical reasoning can lead to correct conclusions, but incorrect predictions about reality. Level 6. The Sorites paradox, or heap paradox. A single grain of sand is not a heap. I think we can all agree on that. One grain sitting on a table is just one grain. It's definitely not a heap. Now, if you have something that's not a heap, and you add just one single grain of sand to it, it's still not a heap. One grain cannot possibly make the difference between not a heap and a heap. That seems obviously true. So let's start our reasoning. One grain, not a heap. Add one grain, now we have 2 grains, still not a heap. Add another grain, now 3 grains, still not a heap. 4 grains, definitely not a heap. We can keep applying this exact same logic, 1 grain at a time. 5 grains, not a heap. 10 grains, not a heap. 20 grains, not a heap. 100 grains, not a heap. Each time we add 1 grain, it's still not a heap, because 1 grain can never transform a non-heap into a heap. But if we continue this reasoning consistently, we reach an absurd conclusion. 1,000 grains of sand, not a heap. 10,000 grains, not a heap. 1,000,000 grains, not a heap. By our logic, no matter how many grains of sand we pile up, we can never have a heap. 100 billion grains of sand, enough to fill a room, would still not be a heap. Yet we know that large collections of sand definitely do form heaps. We could look at a pile of sand and recognize it as a heap. So where exactly does the transformation happen?
At which precise grain does a non-heap become a heap? After grain number 34,582? Why that grain and not the one before? This is the Sorites paradox, from the ancient Greek word soros, meaning heap. It reveals a profound problem with vague concepts. Most of our everyday concepts are vague: bald versus hairy, tall versus short, rich versus poor, old versus young. They don't have sharp boundaries. When does a person become bald? After losing 1 hair? 10 hairs? Where's the line? When does a child become an adult? At midnight on their 18th birthday? 1 second before midnight they're a child, 1 second after an adult? The paradox shows that reality doesn't always fit into neat categories. Vagueness is a fundamental feature of how we understand the world. Some philosophers argue we need to accept fuzzy boundaries and degrees of truth. Others believe there are precise boundaries, but we just don't know where they are. The Sorites paradox remains one of the most challenging puzzles in logic and language.
Level 7. The grandfather paradox. Imagine that scientists finally invent a working time machine. You step inside, set the controls, and travel back to the year 1935, decades before you were born. You arrive successfully in the past and begin exploring this earlier world. While walking through a city in the past, you encounter a young man. Through an improbable but not impossible series of events, you accidentally cause this man's death. Later, you discover something horrifying. This man was your grandfather. And this happened before your grandfather met your grandmother, before your parents were ever born. Now think about what this means. If your grandfather died before your parents were born, then your parents never existed. And if your parents never existed, then you never existed. You were never born. But if you were never born, then you couldn't have traveled back in time in the first place. You couldn't have been there to cause your grandfather's death. So your grandfather would have lived, met your grandmother, had your parents, and you would have been born after all. Which means you could travel back in time and prevent your grandfather from having children. Do you see the loop? We're caught in an impossible contradiction. You simultaneously must exist and must not exist. You must have traveled back in time and must not have traveled back in time. The entire chain of causality becomes circular and self-contradictory. This is the grandfather paradox, one of the most famous arguments against the possibility of backwards time travel. If you can change the past, you can create these logical contradictions. But the universe doesn't allow logical contradictions to exist, at least not in our everyday experience. Scientists and philosophers have proposed various solutions. Maybe the universe prevents you from changing the past. Every time you try to harm your grandfather, something stops you. Maybe time travel creates parallel universes, so you kill an alternate version of your grandfather in a different timeline. Maybe the past is immutable. Everything you do in the past already happened and is part of the timeline that led to your existence. Or maybe the paradox simply proves that backwards time travel to a changeable past is fundamentally impossible. The laws of physics might simply forbid it. The grandfather paradox forces us to confront deep questions about causality, free will, and the nature of time itself. Can effects precede their causes? Is the past fixed or fluid? The paradox suggests that time might not work the way our intuitions tell us it does. Let's consider the concept of an omnipotent being, a being with unlimited power, capable of doing absolutely anything. Many religious traditions describe their deity as omnipotent. It's a central concept in theology and philosophy. But omnipotence contains a hidden logical problem. Here's the question. Can an omnipotent being create a stone so heavy that even they cannot lift it. Take a moment to think about this carefully. If the being can create such a stone so massive, so heavy, so incredibly weighted that it exceeds even their power to lift, then we've identified something this being cannot do. They cannot lift that stone. The existence of such a stone means there's a limit to their power. They're not omnipotent after all. But what if the being cannot create such a stone? What if there's no stone they can create that would be too heavy for them to lift? Then we've still identified something they cannot do. They cannot create this particular stone. The inability to create it means they have a limitation. Again, they're not truly omnipotent. Either way we go, we arrive at a contradiction. If they can create the stone, they're not omnipotent because they can't lift it. If they can't create the stone, they're not omnipotent because they can't create it. Omnipotence itself seems to be a logically impossible concept. Theologians and philosophers have debated this paradox for centuries. Some argue omnipotence doesn't mean the ability to do logically impossible things. God can't create square circles or married bachelors because these aren't actually things, they're just contradictions wrapped in words. Similarly, a stone too heavy for an omnipotent being to lift might just be word salad, a pseudo-concept that seems meaningful but isn't. Others suggest the question itself is flawed. It's like asking what happens when an irresistible force meets an immovable object. The scenario assumes two contradictory absolutes can exist simultaneously, which makes the question meaningless. Still others argue this paradox reveals genuine limits to the concept of omnipotence, suggesting we need to refine how we think about ultimate power. Perhaps omnipotence means having all powers that can logically coexist, rather than the ability to do absolutely anything, including the logically impossible. The omnipotence paradox shows us that infinity and absolute concepts strain the limits of logic and language. Some ideas might be too large for logical frameworks to contain. Whether that tells us something about the limits of logic or the limits of omnipotence remains an open question.
Level 9. The Bootstrap Paradox. Imagine you're a devoted fan of Beethoven. You own a complete collection of his musical scores. One day, scientists unveil a working time machine, and you immediately know what you want to do. Meet Beethoven himself, the greatest composer who ever lived. You travel back in time to the year 1800, carrying with you the sheet music for Beethoven's Fifth Symphony. When you arrive in the past, you search for the young composer and find him, but you discover something unexpected. This younger Beethoven hasn't written any of his masterpieces yet. He's just a struggling musician. You make a decision. You give him the sheet music for the Fifth Symphony. Beethoven looks at it, amazed by its brilliance. He copies it carefully, note for note. Later, he publishes it under his own name. It becomes one of the most famous pieces of music in history. Centuries later, you find that published version and bring it back in time to give it to him. Now, here's the disturbing question. Who actually composed Beethoven's Fifth Symphony? Think about it carefully. You got the sheet music from Beethoven's published works, but Beethoven only published it because you gave it to him. He copied what you gave him, but you only had it to give him because he had published it. The music exists in a perfect closed loop through time. The composition was never actually created. There was no moment of inspiration, no pencil touching paper for the first time, no creative process. The information simply exists, being passed in a circle through time with no point of origin. The symphony has no composer. It's an effect without a cause. This is called the bootstrap paradox, also known as a causal loop or an ontological paradox. The name comes from the phrase pulling yourself up by your bootstraps, doing something impossible without external help. Information or objects exist without ever being created, without ever having a beginning. The paradox appears often in time travel stories, but it reveals something profound about causality. We assume everything must have a cause, everything must come from somewhere. Effects follow causes in a clear linear sequence. But if time travel is possible, information could exist in these causeless loops. Some physicists argue this means time travel is impossible. The universe won't permit these causeless loops. Others suggest these loops might actually be possible, challenging our assumptions about causality. Still others propose that quantum mechanics might resolve the paradox in ways we don't yet understand. The bootstrap paradox shows us that time travel creates problems far stranger than simple contradictions. It's not just about what could happen, it's about whether meaning and origin can exist at all in a universe with time loops.
Level 10. The Paradox of the Ravens. Science works through observation and evidence. If you want to test the hypothesis, all ravens are black, you go out and observe ravens. Each time you see a black raven, it provides evidence supporting your hypothesis. This is basic scientific methodology. Simple, logical, straightforward. But here's where things get strange. The statement, "all ravens are black," is logically equivalent to saying all non-black things are non-ravens. These two statements mean exactly the same thing, just expressed differently. If one is true, the other must be true. They're logically interchangeable. So if observing a black raven provides evidence for all ravens are black, then observing a non-black non-raven should provide evidence for all non-black things are non-ravens, which is the same hypothesis. This means that when you look at a green apple, you're gathering evidence about ravens. Think about what this implies. You're sitting in your kitchen eating a green apple. That apple is not black and it's not a raven. According to the logic, observing this green apple provides evidence, however slight, that all ravens are black. The blue chair you're sitting on provides evidence. The red car outside your window provides evidence. Everything in the universe that's not a black raven provides evidence for the hypothesis. This feels absurd. How can looking at apples, chairs, and cars tell us anything about ravens? Yet the logic is perfectly valid. The reasoning is sound. Each step follows necessarily from the previous one. This is the raven paradox, formulated by philosopher Carl Hempel in the 1940s. It's also called Hempel's paradox or the paradox of confirmation. It reveals a deep problem with scientific reasoning and how evidence actually works. The paradox has generated dozens of proposed solutions. Some argue that non-black non-ravens do provide evidence, but very tiny amounts because there are so many non-black things in the universe. Others say evidence depends on what question you're asking. Looking for ravens provides different information than categorizing objects in your kitchen. Still others argue this shows that logical equivalence doesn't guarantee evidential equivalence. Two statements can mean the same thing logically, but have different evidential relationships to observations. The Raven paradox teaches us that scientific confirmation is more subtle and complex than simple accumulation of consistent observations. It shows that even our most basic intuitions about evidence and proof may need serious refinement.
Level 11. The Crocodile Dilemma. An ancient crocodile catches a child playing by the river. The parent rushes over, desperate to save their child. The crocodile, being a philosophical crocodile, makes an offer. "I will ask you one question," the crocodile says. "If you answer correctly, I will return your child unharmed. If you answer incorrectly, I will keep your child." Here is the question. Will I return your child to you? The parent thinks carefully. They could say, "Yes, you will return my child." But if they're wrong, the crocodile keeps the child. That's too risky. So the parent says, "You will not return my child." Now, the crocodile faces an impossible situation. Let's think through what happens. If the parent answered correctly, if the crocodile truly will not return the child, then according to the deal, the crocodile must return the child because they answered correctly. But if the crocodile returns the child, then the parent's answer was actually wrong. The crocodile said it wouldn't return the child, but it did. But what if the parent answered incorrectly? If the crocodile was actually going to return the child, then the parent's answer, "You will not return my child," was wrong. According to the deal, the crocodile keeps the child. But if the crocodile keeps the child, then the parent's answer was actually correct. The crocodile did not return the child. Either way, the crocodile is trapped. If the answer is correct, following the rule makes it incorrect. If the answer is incorrect, following the rule makes it correct. This is the crocodile dilemma, an ancient Greek paradox. It's similar to the liar paradox, but it involves a promise and a prediction, making it about future actions rather than just truth values. The paradox reveals something important about self-referential promises and predictions. When a promise depends on predicting whether the promise will be kept, logical contradictions emerge. This has real implications for contracts, legal agreements, and even computer programming. Any system that allows rules to reference their own outcomes can potentially create these impossible situations. The crocodile paradox shows us that some questions have no logically consistent answer, not because we're not smart enough to find it, but because the question itself creates an impossible loop.
Level 12. The paradox of the court. Protagoras paradox.
In ancient Greece, a law teacher named Protagoras made a deal with his student. The student couldn't afford to pay for his legal education up front, so they agreed on special terms. Protagoras would teach the student everything about law. In return, the student would pay Protagoras his fee only after winning his first case in court. If the student never won a case, he would never have to pay. It seemed like a fair arrangement. The teacher gets paid when the student proves the education was worthwhile. Years pass. The student completes his education but never takes a case to court. He simply doesn't practice law. Protagoras waits, but no payment comes. Finally, Protagoras loses patience. He decides to sue his former student for the tuition fee. They go to court. Now, think about what happens next. If Protagoras wins the case, then by the court's decision, the student must pay him. But if the student loses this case, then he has still never won a case in court. According to their original agreement, he doesn't have to pay until he wins his first case. So the court's order to pay contradicts the contract. But what if the student wins the case? If the student wins, the court rules that he doesn't have to pay Protagoras. But if he wins this case, then he has won his first case in court. According to the original agreement, he now must pay Protagoras. So winning means he must pay, even though the court just ruled he doesn't have to. Either outcome creates a contradiction. Win or lose, the student both must pay and must not pay. This is the paradox of the court, also called Protagoras paradox. It reveals a problem with self-referential contracts, agreements whose conditions depend on the outcome of disputes about the agreement itself. This paradox has real relevance in modern law.
It shows why legal systems need to be carefully structured to avoid circular dependencies. Contract law today includes principles specifically designed to prevent these kinds of logical traps, ensuring that the resolution of a dispute doesn't create new contradictions in the original agreement.
Imagine a society that values tolerance above all else. This society believes in accepting different viewpoints, different lifestyles, different beliefs. Tolerance is the foundation of everything. Everyone should be free to think and express themselves as they choose. This sounds noble and good, a truly tolerant society. But now a group emerges within this society that actively promotes intolerance. They spread ideas that certain people should not be tolerated. They advocate for restricting the freedoms of others. They want to build a movement based on excluding and suppressing different groups. The tolerant society faces a dilemma. Should they tolerate this intolerant group? If the society tolerates the intolerant group, allows them to spread their message and gain power, then eventually this intolerant group might become strong enough to destroy tolerance itself. By tolerating intolerance, tolerance leads to its own extinction. The very openness that defines the society becomes the weapon used to destroy it. But if the society does not tolerate the intolerant group, if they suppress these voices, ban their speech, exclude them from public discourse, then the society has become intolerant. They violated their own core principle. They're no longer a truly tolerant society. Either way, pure tolerance fails. Unlimited tolerance leads to the disappearance of tolerance. But limiting tolerance means tolerance was never unlimited in the first place. This is the paradox of tolerance, articulated by philosopher Karl Popper. It's not just a thought experiment. It's a real dilemma that democratic societies face constantly when dealing with extremist movements, hate speech, and anti-democratic groups. Popper's conclusion was that for tolerance to survive, a tolerant society must be intolerant of intolerance itself. But this immediately raises new questions. Who decides what counts as dangerous intolerance versus legitimate disagreement? Where do we draw the line? The paradox reveals that even our most cherished values contain internal tensions. Perfect tolerance is logically impossible. Every open society must, at some point, decide what it will not tolerate. The paradox doesn't give us the answer, but it shows us that some form of boundary is inevitable.
Level 14. The Bootstrap Paradox. Information Loop. A woman loves Shakespeare. She owns a complete collection of his plays. One day, she gains access to a time machine and decides to meet her idol. She travels back to the year 1590 to Stratford-upon-Avon, carrying a book containing Hamlet. When she arrives, she searches for Shakespeare. She finds him, a young man who hasn't written his famous plays yet. He's just a struggling actor. She makes a decision. She gives him the book containing Hamlet. Shakespeare reads it, amazed. He copies it word for word. Later, he publishes it under his name. It becomes one of the greatest plays ever written. Centuries later, our time traveler finds that published version, puts it in her collection, and brings it back in time to give to Shakespeare. Now, here's the question that should bother you. Who wrote Hamlet? The time traveler didn't write it. She just copied an existing book. Shakespeare didn't write it. He just copied what the time traveler gave him. The play was never created. It has no author. It exists in a perfect closed loop through time, being passed back and forth with no origin point. The information simply exists eternally with no creation event. No one ever sat down and composed those famous lines, "to be or not to be." The words just are, flowing in a circle through time. This is the bootstrap paradox, also called a causal loop. The name comes from the impossible phrase, pulling yourself up by your bootstraps, creating something from nothing.
This paradox appears in countless time travel stories, but it reveals something deeper about causality and information. We assume everything must have a beginning, that information must be created somewhere. But if time travel is possible, information could exist in these authorless loops. Some physicists argue this proves time travel is impossible. The universe won't permit causeless information. Others suggest these loops might actually be allowed by the laws of physics. The paradox even connects to questions in quantum mechanics about whether information can truly be created or destroyed. The bootstrap paradox forces us to confront a disturbing possibility. In a universe with time loops, some things simply exist, with no creator, no origin, no explanation. They just are, cycling endlessly through time.
Level 15. The arrow paradox. An arrow is shot from a bow. It flies through the air toward its target. We can all see this happening. Motion is real and obvious. But the ancient Greek philosopher Zeno asked us to think more carefully about what's actually happening. At any single instant in time, any single frozen moment, where is the arrow? It occupies a specific position in space. At that instant, the arrow is simply there at that location. Now here's Zeno's question. At that instant, is the arrow moving? Think about it. An instant has no duration. It's not a period of time, it's a single point in time. For something to move, it must be in one place and then be in another place. But that requires time to pass. During a single instant, no time passes. So at any given instant, the arrow is not moving. It's simply at a position, motionless, frozen in space. But time is made up of instants. Time is just a collection of these individual moments, one after another. If the arrow is motionless at every single instant, and time is just a collection of instants, then the arrow is motionless throughout the entire time period. Motion is impossible. Yet we clearly see the arrow flying through the air and hitting the target. This is Zeno's arrow paradox. Zeno wasn't denying the reality of motion. He could see things move just like anyone else. He was showing that our logical understanding of time and motion leads to a contradiction. The paradox reveals deep problems with how we think about time. Is time really made of discrete instants, like frames in a film? Or is time continuous, infinitely divisible, not actually composed of separate moments? Modern physics suggests that motion is fundamental. It's not built up from static moments. Velocity exists at an instant, even though we usually define velocity as distance over time. Calculus, invented thousands of years after Zeno, gives us mathematical tools to handle instantaneous rates of change. But Zeno's paradox still haunts physics. At the quantum level, questions about whether space and time are continuous or discrete remain unresolved. The arrow paradox shows us that motion, something we take completely for granted, is far stranger than it appears.
Level 16. The paradox of fiction. You're watching a movie. The protagonist's child dies in a tragic accident. You feel your chest tighten, your eyes water, tears run down your face. You are genuinely sad. Real sadness, real tears, real emotion. But you know it's not real. You know the protagonist is an actor. You know the child is fine, probably eating snacks between takes. You know the entire story is made up. None of it happened. These people don't exist. Yet you cry anyway. Here's the paradox. How can you feel real emotions about something you know is not real? We normally have emotional responses to things we believe are actually happening. You feel fear when you believe there's real danger. You feel joy when you believe something good has actually happened.
Emotions are triggered by beliefs about reality. But when you watch fiction, you don't believe it's real. You're not confused about whether the movie actually happened. You know it's invented, acted, edited, created for entertainment. You believe these events never occurred and these people never existed. So why do you care? Why does fiction move us so deeply? Why do we cry at sad movies, cheer for characters in books, feel angry at villains in stories we know are made up? This is the paradox of fiction. Our emotional responses seem to require belief, but fiction generates powerful emotions without belief. Philosophers have proposed several solutions. Some say we temporarily suspend our disbelief and quasi-believe the story is real while experiencing it. Others argue that emotions don't actually require belief. Imagination alone is enough to trigger genuine feelings. Still others suggest we're not responding to the specific fictional events, but to real, universal human experiences and truths that the fiction represents. The paradox reveals something profound about human psychology. Our emotional systems don't neatly separate fact from fiction. Stories shape us, teach us empathy, and allow us to experience situations we'll never actually face. Fiction might be one of our most powerful tools for understanding reality, precisely because our emotions treat it as real. This isn't a bug in human psychology. It might be a feature. Our ability to emotionally engage with fiction could be what allows us to learn from others' experiences, develop empathy, and simulate scenarios before facing them in real life.
Level 17. The unexpected exam paradox. A teacher tells her students on Friday, "Sometime this coming week, Monday through Friday, you will have a surprise exam. You will not know which day the exam is on until you arrive at class that morning." A clever student begins to reason through this. The exam cannot be on Friday, because if we reach the end of Thursday without having had the exam, we'll know with certainty it must be Friday. But then it wouldn't be a surprise, so Friday is impossible. She continues, "Since Friday is eliminated, Thursday is now the last possible day. But if we reach the end of Wednesday without an exam, we'll know it must be Thursday. Again, no surprise. So Thursday is also impossible." She applies this logic backward through the week. Wednesday is impossible for the same reason. Tuesday is impossible. Monday is impossible because we'd know right now that it has to be Monday since all other days are eliminated. The student concludes that a surprise exam is logically impossible and stops studying. Wednesday morning arrives. The teacher hands out the exam. The student is genuinely surprised. But wait, her logic seemed perfect. Each step followed from the previous one, yet her conclusion was completely wrong. Where did the reasoning fail? This is the unexpected exam paradox, also called the surprise test paradox. It's similar to the unexpected hanging, but the classroom setting makes the logic feel even more intuitive and the failure more puzzling. The error is subtle and has sparked decades of debate among logicians. The problem involves reasoning about your own future knowledge. The student assumes that if she survives to Thursday without an exam, she'll know the exam is on Friday. But that assumption itself depends on trusting the backward elimination logic. Once she concludes the exam is impossible and stops expecting it, she can be surprised on any day, including Friday. The paradox reveals deep issues with self-referential reasoning and predictions about surprise. It shows that certain kinds of logical arguments can be valid step by step, but still lead to false conclusions when they involve predicting your own future state of knowledge. This has implications for game theory, decision theory, and even artificial intelligence.
Systems that reason about their own future beliefs can create these logical loops that defeat themselves.
Level 18. The paradox of hedonism. You want to be happy. Happiness is your goal, perhaps the most important goal in your life. So you pursue it directly. You seek out pleasurable experiences. You organize your day around maximizing your happiness. You constantly ask yourself, am I happy? How can I be happier? This seems perfectly logical. If you want something, you should pursue it. But here's what happens. The more directly you chase happiness, the more it slips away from you. The harder you try to be happy, the less happy you become. People who make happiness their primary goal often end up anxious, self-absorbed, and ultimately less happy than when they started. Meanwhile, people who pursue other goals, helping others, creating something meaningful, mastering a skill, building deep relationships, often find that happiness comes to them naturally, without effort. They weren't trying to be happy. They were absorbed in something else, yet happiness arrived as a side effect. This is the paradox of hedonism, also called the pleasure paradox. Happiness cannot be obtained by pursuing it directly. The very act of chasing happiness prevents you from achieving it. Why does this happen? When you focus on your own happiness, you become self-conscious and analytical. You're constantly monitoring your emotional state, comparing it to some ideal, finding it lacking. This self-focused attention destroys the spontaneous, unself-conscious experience that actually creates genuine joy. It's similar to trying to fall asleep. The harder you try, the more awake you become. Effort defeats the goal. Real happiness seems to come from self-forgetting, from being absorbed in something beyond yourself. When you stop asking, "Am I happy?" and instead lose yourself in meaningful activity, happiness emerges naturally. This paradox has practical implications. It suggests that self-help culture's focus on pursuing personal happiness might actually be counterproductive. Instead of asking, "What will make me happy?" we might need to ask, "What's worth doing?" and trust that happiness will follow. The ancient philosophers knew this. Aristotle argued that happiness comes from living virtuously and engaging in meaningful activities, not from pursuing pleasure directly. The paradox of hedonism suggests they were onto something profound about human psychology.
Level 19. The lottery paradox. A lottery has 1 million tickets. Only one ticket will win. You hold ticket number 500,042. You rationally believe that your ticket will not win. The odds are 1 in a million. It would be irrational to believe you'll win, so you believe you'll lose. This seems perfectly reasonable. Now apply the same reasoning to every other ticket. Ticket number 1 has a 1 in a million chance. You rationally believe it will lose. Ticket number 2 will lose. Ticket number 3 will lose. For each individual ticket, the rational belief is that it will lose. If you're rational, you believe that ticket 1 will lose, ticket 2 will lose, ticket 3 will lose, and so on for all 1 million tickets. But now you hold a set of beliefs that includes all 1 million tickets will lose. Yet you also know with absolute certainty that exactly one ticket must win. The lottery will have a winner. You simultaneously believe that all tickets will lose and that one ticket will win. These beliefs contradict each other. This is the lottery paradox formulated by philosopher Henry Kaiberg. It reveals a fundamental problem with rational belief under uncertainty. We think rational people shouldn't hold contradictory beliefs. Consistency is supposed to be a requirement of rationality. But the lottery paradox shows that individually rational beliefs can combine to create collective contradiction. Should we only believe things we're completely certain about?
That seems too restrictive. We'd barely believe anything. Should we believe everything that's highly probable? That leads to contradictions like this lottery situation. The paradox has deep implications for epistemology, the study of knowledge and belief. It questions what it means to rationally believe something. It challenges the idea that we can simply add up probable beliefs and expect them to remain consistent. This isn't just abstract philosophy. The lottery paradox relates to real problems in law, where juries must decide guilt based on probability. It relates to science, where we believe multiple hypotheses that might be individually likely, but collectively incompatible. It shows that rational belief is far more complicated than we assumed.
Level 20. The Sorites Paradox. Revisited. Baldness version. A man has a full head of hair. 100,000 hairs on his head. He is definitely not bald. Everyone would agree, not bald. But over time, he loses one hair. Just one single hair. Is he now bald? Of course not. Losing one hair cannot possibly transform someone from not bald to bald. He still has 99,999 hairs. He's still not bald. Another hair falls out. Is he bald now? No, still not bald. One hair doesn't make that difference. We can continue this reasoning. Losing one hair never makes someone bald if they weren't bald before. The difference between 90,000 hairs and 89,999 hairs can't be the difference between not bald and bald. But if we follow this logic consistently, we reach an absurd conclusion. Even when the man has only 10 hairs left, he's not bald. Even when he has one hair, he's not bald. Even when he has 0 hairs, completely smooth scalp, he's still not bald, because we never crossed a threshold where losing one hair made him bald. Yet we know that a man with 0 hairs is definitely bald. So where is the line? After losing which specific hair does someone become bald? Hair number 67,412. Why that one? What makes that particular hair special? This is the Sorites paradox, ancient Greek for paradox of the heap. It applies to any vague concept where there's no sharp boundary. When does a child become an adult? When does someone become tall? When does someone become rich? When does a language become dead? All these concepts are vague, with fuzzy boundaries, yet we use them constantly. The paradox reveals something fundamental about how human language and thought work. Most of our categories are not precise. They have borderline cases where we genuinely can't say whether something fits the category. Some philosophers argue we need to accept degrees of truth. Someone can be somewhat bald or 70% bald. Others argue there are precise boundaries, but we just don't know where they are. Still others say vagueness is a fundamental feature of reality itself, not just our language. The Sorites paradox shows that the world doesn't always fit into neat categories. Gray areas aren't just annoying, they're unavoidable features of how we conceptualize reality.
Level 21. The paradox of the proof script. A mathematics professor writes a theorem on the board. She tells her students, "This theorem cannot be proven." A student raises his hand and asks, "How do you know it can't be proven?" The professor responds, "I can prove it cannot be proven." Wait, think about what just happened. If the professor can prove that the theorem cannot be proven, then she has just proven something about the theorem. She's demonstrated a mathematical truth, that this particular theorem has no proof. But that demonstration itself is a proof. She proved something. So if she successfully proves that the theorem cannot be proven, then she has proven the theorem by proving it has no proof. But if the theorem can be proven, then her claim that it cannot be proven is false. The proof defeats itself.
But what if she's wrong? What if she cannot actually prove that the theorem cannot be proven? Then maybe the theorem can be proven after all, but we don't know. This is a simplified version of the kind of self-referential problem that Kurt Gödel encountered in his famous incompleteness theorems. Gödel showed that in any mathematical system complex enough to include basic arithmetic, there are true statements that cannot be proven within that system. The revolutionary insight was that you can construct a mathematical statement that essentially says, this statement cannot be proven. If the statement is true, then it really cannot be proven, but that means it's a true statement with no proof. If it can be proven, then what it says is false, but mathematical proofs only prove true things, so we have a contradiction. Gödel's work shattered the dream of a complete, consistent mathematical system where every truth could be proven. It revealed fundamental limits to formal logical systems. Some truths exist beyond the reach of proof. This has profound implications. It means mathematics will always be incomplete. There will always be true statements we cannot prove. It influenced computer science, showing that some problems are fundamentally unsolvable. It even influenced philosophy, raising questions about the nature of truth itself. The paradox of the proof shows that proof, our most powerful tool for establishing certainty, has inherent limitations built into its very structure.
Level 23. Newcomb's Paradox. A super-intelligent being approaches you. This being has never been wrong in thousands of predictions about human behavior. It presents you with two boxes. Box A is transparent. You can see it contains $1,000. Box B is opaque. You cannot see inside. It contains either $1 million or nothing. You have two choices. Take both boxes or take only box B. Here's the twist. Yesterday, the being predicted what you would choose today. If it predicted you would take only box B, it put $1 million in box B. If it predicted you would take both boxes, it left box B empty. The being has played this game with thousands of people and has never been wrong. People who took only box B walked away with $1 million. People who took both boxes found box B empty and got only $1,000. What should you do? One argument says, take both boxes. The money is already in the boxes or not. Your choice now cannot change the past. Whether box B contains money was determined yesterday. So you should take both boxes. You'll get the $1,000 plus whatever is in box B. Taking both is strictly better than taking only one. But another argument says, take only box B. The evidence is overwhelming. Everyone who took both boxes got only $1,000. Everyone who took only box B got $1 million. The being's prediction is essentially perfect. If you take both boxes, box B will be empty. If you take only box B, it will contain $1 million. Both arguments seem valid, yet they give opposite answers. This is Newcomb's paradox, created by physicist William Newcomb. It has generated fierce debate for over 50 years. Brilliant thinkers disagree about the right answer. The paradox pits two types of decision theory against each other. Causal decision theory says take both boxes. You can't change the past, so take everything available. Evidential decision theory says take only box B. Your choice is evidence of what the being predicted, so choose the action correlated with the best outcome. The deeper question is about free will and determinism. If the being can predict your choice with perfect accuracy, are you really free to choose? Or is your choice predetermined by the brain state the being observed? Newcomb's paradox forces us to confront what it means to make a rational decision when facing a perfect predictor. Level 24. The paradox of preface. A scientist spends 10 years researching climate patterns. She writes a comprehensive book containing 100 specific claims, each supported by careful research. She believes each claim is true. That's why she published them. In the preface, being intellectually honest, she writes, "I have tried to be accurate throughout this book, but given the complexity of the subject and the limits of human knowledge, I'm sure this book contains some errors. Some of my claims are probably wrong." Now, think about what she's saying. She believes claim 1 is true. She believes claim 2 is true. She believes claim 3 is true. All the way through 100 claims, she believes each one is true. But she also believes that some of these claims are false. She's certain the book contains errors. She simultaneously believes that each individual claim is true and that some claims are false. These beliefs contradict each other. Is she being irrational? No, she's being perfectly reasonable. It would be arrogant to claim her book contains no errors. Given the complexity of the subject and human fallibility, some mistakes are inevitable. But this reasonableness creates a logical problem. Rational belief requires consistency. You shouldn't believe contradictory things. Yet here, being rational and humble seems to require believing a contradiction. This is the preface paradox, formulated by philosopher David Mackinson. It's closely related to the lottery paradox, but adds the element of intellectual humility. The paradox reveals tension between two types of rationality. It's rational to believe each well-supported claim. It's also rational to believe you've made some mistakes somewhere. But holding both beliefs creates inconsistency. Some philosophers argue we should distinguish between belief in individual claims and meta-level beliefs about our overall reliability. Others say this shows that rational belief doesn't require absolute consistency. Some contradictions are acceptable when they arise from appropriate humility. The preface paradox has practical implications. Scientists, historians, and experts regularly face this situation. They must assert claims while acknowledging fallibility. The paradox shows that intellectual honesty can generate logical tension. It also connects to questions about scientific progress. Science advances by maintaining confidence in current theories while remaining open to the possibility that we're wrong. The preface paradox suggests this attitude, though seemingly contradictory, might be epistemically necessary.
Level 25. The paradox of omniscience. God, in traditional theology, is omniscient. This means God knows everything. All truths, all facts. Everything that has happened, is happening, or will happen. Complete, perfect knowledge. But consider this question. Can God create a stone so heavy that he cannot lift it? We've seen this paradox before regarding omnipotence, but now let's approach it through omniscience. If God is omniscient, God knows the answer to this question right now. God knows whether he can create this stone or not, so there's a definite answer. Suppose the answer is yes, God can create such a stone. Then God knows that he can create this stone. But if he creates it and cannot lift it, then there's something God cannot do. He's not omnipotent. Suppose the answer is no, God cannot create such a stone. Then God knows he cannot create it. But then there's something God cannot know how to do. His knowledge has a limit. But here's a deeper problem. If God knows everything that will happen in the future, then the future is already determined. God knows right now what you'll choose to have for breakfast tomorrow. That knowledge is part of God's perfect omniscience. But if God knows what you'll choose, can you choose differently? If you could choose differently, then God's knowledge would be wrong. But God's knowledge cannot be wrong. That contradicts omniscience. So your choice is predetermined. You cannot do anything other than what God already knows you will do. But if you cannot choose differently, do you have free will?
This is the paradox of omniscience. Perfect knowledge seems incompatible with free will. If God knows all future choices, those choices are fixed. If choices are truly free and could be otherwise, then God cannot know with certainty what they'll be. Theologians have struggled with this for centuries. Some argue that God exists outside time, knowing all moments simultaneously, so divine foreknowledge doesn't cause human choices. Others suggest God knows all possibilities, but not which one you'll actualize. Still others accept that free will, as commonly understood, is an illusion. The paradox reveals deep tensions in how we think about knowledge, time, and freedom. Even without theology, it raises questions. If the universe is deterministic, can knowledge of future states coexist with meaningful choice?
Level 26. The paradox of the stone. Alternate form. Here's a simpler question than divine omnipotence. Can you make a promise you cannot break? Think about it. A promise is a commitment to do something, but you're free to break promises. That's what makes trustworthiness valuable. You could break any promise, but you choose not to. But what if you promise, I promise that I will break this promise? If you keep the promise, then what the promise says comes true. You break the promise. But if you break it, then you've done what you promised, which means you kept it. The promise cannot be kept without being broken, and cannot be broken without being kept. This is a version of the liar paradox applied to actions rather than statements. It reveals that self-reference creates impossible situations, not just in language, but in commitments and actions. Now scale this up. Can an all-powerful being create a rule it cannot break? If it can create such a rule, then the rule limits its power. It's bound by something. But if it cannot create such a rule, then there's something it cannot do. Create that particular binding rule. This version of the stone paradox focuses on self-limitation rather than physical impossibility. Can ultimate power limit itself? If it can, it's no longer ultimate. If it cannot, it has a limitation. The paradox reveals something about the nature of power and freedom. We value freedom, but meaningful commitments require giving up freedom. Marriage, careers, values, all involve self-limitation. The stone paradox suggests that the tension between freedom and commitment might be fundamental to what power and choice mean.
Level 27. Simpson's paradox. A hospital is testing two treatments for a disease, treatment A and treatment B. They want to know which is more effective. They run studies. In the study of patients with mild cases, treatment A cures 80 out of 100 patients. Treatment B cures 60 out of 75 patients. Treatment A is better for mild cases. In the study of severe cases, treatment A cures 20 out of 50 patients. Treatment B cures 10 out of 25 patients. Treatment A is better for severe cases too. So treatment A is better for mild cases and better for severe cases. Clearly, treatment A is the better treatment overall, right? But when you combine all the patients together, something strange happens. Treatment A cured 100 out of 150 patients total. That's 67%. Treatment B cured 70 out of 100 patients total. That's 70%. Treatment B has a higher overall success rate, even though treatment A was better for every individual subgroup. How is this possible? This is Simpson's paradox,
a statistical phenomenon where a trend appears in different groups of data but disappears or reverses when the groups are combined. The resolution involves understanding that the groups have different sizes and different base rates. Treatment A was tested on many more patients, and a larger proportion of those patients had severe cases, which are harder to treat. Treatment B was tested on fewer patients with a higher proportion of mild cases. When you combine the data without accounting for these differences in group composition, you get a misleading result. Simpson's paradox appears constantly in real-world data. It affects medical research, social science studies, business analytics, and legal statistics. It's why correlation doesn't imply causation, and why good statistics requires careful analysis of subgroups. The paradox shows that data can tell opposite stories depending on how you aggregate it. Two true statistical facts can seem to contradict each other. This has serious implications. Judges have made wrong decisions, medical treatments have been misunderstood, and social policies have been misdirected because of Simpson's paradox. It reveals that statistical truth is not straightforward. Numbers don't speak for themselves. The same data, honestly reported, can support opposite conclusions depending on how you group and analyze it. Understanding statistics requires understanding what the numbers are actually measuring and what populations they represent.
Level 28. The paradox of blackmail. You discover something embarrassing about your neighbor. Maybe they had an affair. You have evidence. It's true. You have every legal right to tell people this information. Free speech protects your right to share true facts. You could tell their spouse, their employer, their friends. That's completely legal. Your neighbor would prefer you didn't tell anyone. They'd be willing to pay you to keep quiet. You also have every legal right to ask your neighbor for money. You can request payment for services, for goods, for whatever you want. Asking for money is not illegal. But if you say to your neighbor, "Pay me money or I'll tell everyone your secret," that's blackmail. That's a serious crime. Here's the paradox. You have the legal right to do action A, reveal the information. You have the legal right to do action B, ask for money. But combining those rights, offering to refrain from A in exchange for B, is illegal. How can the combination of two legal actions create an illegal action? How can doing A or doing B be legal, but making their connection explicit become criminal? This is the paradox of blackmail. It puzzles legal scholars because blackmail seems to criminalize the ordinary exchange of rights. You're essentially selling your right to speak, which you own. Some argue that blackmail is wrong because it's exploitative. You're profiting from another's vulnerability. But many legal transactions involve someone profiting from another's needs. Lawyers charge people in desperate situations. That's not illegal. Others suggest that blackmail should not actually be illegal, that its criminalization is a historical accident without good justification. If you have the right to speak and the right to refrain from speaking, you should have the right to negotiate which of those actions you take. The paradox reveals something interesting about rights and markets. Not everything should be for sale, even if we have rights over it. Some connections between actions are appropriate to make explicit, others are not. The boundary between legitimate negotiation and wrongful coercion is not as clear as we might think. Level 28. The paradox of blackmail. You discover something embarrassing about your neighbor. Maybe they had an affair. You have evidence. It's true. You have every legal right to tell people this information. Free speech protects your right to share true facts. You could tell their spouse, their employer, their friends. That's completely legal. Your neighbor would prefer you didn't tell anyone. They'd be willing to pay you to keep quiet. You also have every legal right to ask your neighbor for money. You can request payment for services, for goods, for whatever you want. Asking for money is not illegal. But if you say to your neighbor, "Pay me money or I'll tell everyone your secret," that's blackmail. That's a serious crime. Here's the paradox. You have the legal right to do action A, reveal the information. You have the legal right to do action B, ask for money. But combining those rights, offering to refrain from A in exchange for B, is illegal. How can the combination of two legal actions create an illegal action? How can doing A or doing B be legal, but making their connection explicit become criminal? This is the paradox of blackmail. It puzzles legal scholars because blackmail seems to criminalize the ordinary exchange of rights. You're essentially selling your right to speak, which you own. Some argue that blackmail is wrong because it's exploitative. You're profiting from another's vulnerability. But many legal transactions involve someone profiting from another's needs. Lawyers charge people in desperate situations. That's not illegal. Others suggest that blackmail should not actually be illegal, that its criminalization is a historical accident without good justification. If you have the right to speak and the right to refrain from speaking, you should have the right to negotiate which of those actions you take. The paradox reveals something interesting about rights and markets. Not everything should be for sale, even if we have rights over it. Some connections between actions are appropriate to make explicit. Others are not. The boundary between legitimate negotiation and wrongful coercion is not as clear as we might think.
Level 29. The Paradox of Analysis. Revisited. A philosopher wants to analyze what knowledge is. After careful thought, they propose knowledge is justified true belief. If this analysis is correct, then knowledge and justified true belief mean exactly the same thing. They're synonyms. The analysis captures the meaning perfectly. But if they mean exactly the same thing, then the analysis hasn't told us anything new. It's just saying knowledge is knowledge in different words. It's trivial, uninformative. We haven't learned anything. However, if the analysis is informative, if it teaches us something we didn't know before, then it must be telling us something different from what we already understood by knowledge. But if it says something different, then it's not a correct analysis. It has changed the meaning rather than captured it. This is the paradox of analysis. An analysis must be both correct and informative, but being correct means being synonymous with the original term, and being synonymous means not being informative, just saying the same thing differently. How can philosophical analysis teach us anything if correct analysis is just restating what we already knew? The paradox applies to any conceptual analysis. What is justice? What is beauty? What is consciousness? If your answer means exactly what the original term means, you haven't explained anything. If it means something different, you've changed the subject. Some philosophers respond by distinguishing between meaning and understanding. The words might mean the same thing, but the analysis helps us understand the concept better by making its structure explicit. We knew what knowledge was, but the analysis articulates the components we were implicitly using. Others argue this shows that philosophical analysis is impossible. We're just going in circles, using words to define words.
They suggest philosophy should abandon analysis for other methods. Still others say the paradox reveals that meaning is not as simple as we thought. Maybe there's implicit knowledge we possess but cannot articulate. Analysis makes the implicit explicit, which is genuinely informative, even if the meaning stays the same. The paradox of analysis questions whether philosophy can actually make progress through its traditional methods. Can we gain knowledge by analyzing concepts we already understand, or are we just rearranging words without adding insight?
Level 30. Curry's paradox. Consider this sentence. If this sentence is true, then unicorns exist. Let's call this sentence C. Now, let's think through what C claims. C says, if C is true, then unicorns exist. Assume C is true. If C is true, then what it says must be the case. What does it say? It says that if C is true, then unicorns exist. Well, we just assumed C is true, so by the logic of the conditional statement, unicorns must exist. So, if C is true, we can prove that unicorns exist. But we just proved this. If C is true, then unicorns exist. But wait, that's exactly what C says, so we've proven that C is true. And if C is true, then, as we just showed, unicorns exist. We've just proven that unicorns exist, starting from pure logic. Obviously, unicorns don't exist, so something has gone terribly wrong. But where? This is Curry's paradox, named after logician Haskell Curry. Unlike the liar paradox, it doesn't use negation, it just uses a conditional, if-then. Yet it proves anything you want. You can replace unicorns exist with any statement, true or false. If this sentence is true, then the moon is made of cheese. If this sentence is true, then 2 + 2 = 5. The same reasoning proves any conclusion you insert. Curry's paradox is particularly disturbing because it breaks logic using only innocent-looking tools, conditional statements, and self-reference. We use conditionals constantly. They seem harmless, but combined with self-reference, they become weapons that can prove anything. The paradox has forced logicians to rethink fundamental principles. Some systems of logic reject certain rules about conditionals. Others restrict self-reference. Still others modify what it means for a conditional to be true. Curry's paradox shows that the liar paradox is not unique. Self-reference creates problems even without contradiction or negation. Any logical system that allows self-referential conditionals faces the threat of proving everything, which means proving nothing. The system collapses into triviality. This has practical implications for computer science and artificial intelligence. Programming languages must be designed carefully to avoid self-referential structures that could make programs prove false statements or enter infinite loops. Curry's paradox reminds us that logical consistency is fragile and requires constant vigilance. Level 31. The paradox of voting. Election day arrives. You're deciding whether to vote. Your single vote will almost certainly not change the outcome. In a local election, maybe one chance in 10,000. In a national election, maybe 1 in 10 million. Voting takes time. You have to travel to the polling station, wait in line, fill out the ballot, maybe an hour of your time. You could use that hour for something else, something that would definitely benefit you. From a rational self-interest perspective, voting seems irrational. The cost is certain. The benefit is essentially zero. Your vote won't change who wins. Even if you care deeply about the outcome, your individual action makes no measurable difference. Yet millions of people vote, and if everyone reasoned this way and didn't vote, democracy would collapse. The system only works if people act in ways that seem individually irrational. But here's where it gets stranger. Suppose you're not selfish. You care about society. You want the best candidate to win. Should you vote then? If the best candidate is ahead, your vote isn't needed. They'll win without you. If the best candidate is behind, your vote won't help. They'll lose anyway. If the race is exactly tied, your vote breaks the tie. But the probability of an exact tie is infinitesimally small, far smaller than the probability you'll die in a car accident on the way to vote. So even from an altruistic, society-focused perspective, voting seems irrational. The chance your vote matters is smaller than countless other risks you ignore. This is the paradox of voting. Rational choice theory predicts almost no one should vote, yet voter turnout is substantial. People vote in large numbers, despite it being apparently irrational. Economists and political scientists have proposed solutions. Maybe people get intrinsic satisfaction from voting. It feels good to participate. Maybe people follow social norms without calculating costs. Maybe people incorrectly estimate the probability their vote will matter. Maybe voting is rational if you consider not just outcomes, but the symbolic expression of values. The paradox reveals a tension between individual rationality and collective benefit. What's rational for each person individually creates disaster collectively. Democratic participation requires people to act in ways that seem individually pointless. This connects to broader questions about cooperation, social norms, and whether humans are purely rational actors. The fact that people do vote despite the logic suggesting they shouldn't tells us something important about human motivation beyond simple cost-benefit calculation.
Let's consider all natural numbers: 1, 2, 3, 4, and so on, infinitely. Some of these numbers are interesting. Some are boring. 1 is interesting. It's the first number, the multiplicative identity, fundamental to mathematics. 2 is interesting, the only even prime number. 3 is interesting, the first odd prime. 7 is interesting. It appears constantly in culture and mathematics. 13 is interesting, considered unlucky, a prime number. 42 is interesting, the answer to life, the universe, and everything. But surely some numbers are not interesting. They're just ordinary, boring numbers with no special properties. Let's say those numbers form a set, the set of all boring numbers. Now, if there are any boring numbers at all, then there must be a smallest boring number. That's how sets of numbers work. If a set is non-empty, it has a least element. But think about what this means. The smallest boring number would be the very first number that has no interesting properties. That itself is an extremely interesting property. Being the smallest boring number makes it interesting. But if it's interesting, then it's not boring, so it doesn't belong in the set of boring numbers after all. Remove it from the set. Now there's a new smallest boring number. But that number is also interesting for the same reason. It's the smallest boring number, so it must be removed too. This continues infinitely. Every supposedly boring number becomes interesting by virtue of being the smallest boring number. We can never establish any number as truly boring. Conclusion: there are no boring numbers. Every natural number is interesting. This is the paradox of interesting numbers. It's a humorous paradox, but reveals something real about self-reference and definition. The concept of boring is relative and context-dependent. A number's boringness is not an inherent mathematical property, but a judgment that changes based on how we think about it. The paradox shows how classifications can be unstable when the classification itself affects what it's classifying. Being in the category changes whether you belong in the category.
This has philosophical implications beyond numbers. Consider unremarkable people. Is someone who is the most unremarkable person thereby remarkable? Or normal behaviors. If everyone tried to be perfectly normal, would that unusual conformity make them abnormal? The paradox reminds us that some properties are not objective features, but emerge from our perspective and how we categorize things.
You have a letter in your hand. It's sealed in an envelope. There's a moral rule. If you open the letter, you must burn it. This is a conditional obligation. If you do action A, you must do action B. It's a common form of moral reasoning. If you borrow something, you must return it. If you make a promise, you must keep it. Now think carefully. The rule says, if you open the letter, you must burn it. By contrapositive logic, a standard principle of reasoning, this is equivalent to, if you don't burn the letter, you must not open it. So the rule can be rephrased as, you must not open the letter, or you must burn it. This is logically equivalent to the original statement. Both versions say the same thing in standard logic. But now consider what happens if you open the letter and don't burn it. You violated the rule. You opened it, but you didn't burn it as required. According to the rule, if you open the letter, you must burn it, you failed to fulfill an obligation. You did the condition, but not the consequence. But according to the equivalent formulation, if you don't burn the letter, you must not open it, what have you done wrong? You failed to not open it. The wrong action is opening, not failing to burn. Here's where it gets strange. Imagine you haven't opened the letter yet. According to the rule, if you open it, you'll be obligated to burn it. So right now, you have the power to create an obligation for yourself, just by opening the letter. But generally, we think you can't create moral obligations out of thin air just by acting. You can't make murder obligatory by choosing to murder. Yet this conditional rule seems to say you can create the obligation to burn by choosing to open. This is a paradox in deontic logic, the logic of obligation and permission. Conditional obligations create strange situations where you can apparently obligate yourself through voluntary action, and where logically equivalent statements seem to have different moral implications. The paradox reveals that moral reasoning doesn't perfectly map onto standard logical structures. What makes sense in mathematical logic might not make sense in ethics. Obligations and permissions have unique features that resist simple logical formalization.
Level 34. The paradox of inference. You believe that Paris is the capital of France. You've believed this since childhood. It's a fact you're completely confident about. A logician points out, if Paris is the capital of France, then either Paris is the capital of France or the moon is made of cheese. This is valid logic. The statement A or B is true whenever A is true, regardless of whether B is true. So, Paris is the capital of France or the moon is made of cheese is a true statement. But now the logician asks, do you believe that Paris is the capital of France or the moon is made of cheese? You hesitate. The moon isn't made of cheese. Everyone knows that. So this strange disjunctive statement feels wrong to affirm, even though it's technically true. Here's the paradox. You believe Paris is the capital of France. That statement logically implies Paris is the capital of France or the moon is made of cheese. By basic logic, if you believe something and that thing implies something else, you should believe the implication too.
But you don't want to say you believe Paris is the capital of France or the moon is made of cheese. That statement, while technically true, seems to suggest uncertainty about Paris or possibility about the moon's composition. It feels wrong. Yet logic says, if you believe A and A implies B, then you should believe B. This is the principle of belief closure. Your beliefs should be closed under logical implication. The paradox is that belief closure seems to require us to believe strange, misleading statements we would never naturally affirm. Following logic strictly makes our beliefs include countless bizarre disjunctions. Grass is green, or unicorns exist. True, because grass is green, but do you believe it? 2 + 2 = 4, or Napoleon won Waterloo. True, but it's an odd thing to believe. This is the paradox of inference. It shows that human belief is not simply a logical system. We believe in patterns, not as isolated propositions. Understanding belief requires psychology, not just logic.
Two people drink too much at a party. Both make the terrible decision to drive home. Both are equally drunk, equally impaired, equally reckless. The first person drives home on empty streets. By pure chance, no pedestrians are around. They arrive home safely, no harm done. We judge them harshly for drunk driving, but they haven't actually hurt anyone. The second driver, driving the same way, equally drunk, rounds a corner and hits a pedestrian who stepped into the street. The pedestrian dies. The driver is charged with vehicular manslaughter. Both drivers made identical choices. Both had identical intentions. Both were equally reckless and morally wrong in their decision to drive drunk. The only difference is luck, random chance that put a pedestrian in one driver's path but not the other's. Yet, we judge them very differently. The first driver faces minor legal consequences and social disapproval. The second driver faces years in prison, social ostracism, and a lifetime of guilt. We consider the second driver far more morally culpable. But they did the same thing. They made the same choice. The moral quality of their decision was identical. The outcome was determined purely by factors beyond their control, luck. This is the paradox of moral luck. We believe moral responsibility depends on choice, intention, and control. Factors outside your control shouldn't affect how morally responsible you are. Yet, outcomes beyond our control dramatically affect how we judge actions. Consider more examples. A soldier throws a grenade at enemy combatants. One grenade hits its target. We might call it brave action. Another grenade, thrown identically, bounces unpredictably and kills civilians. Now it's a war crime. The throw was the same. Luck determined the outcome. An entrepreneur takes a calculated risk starting a company. One succeeds due to fortunate market timing. They're visionary. Another fails due to a recession. They're reckless. Same decision, different luck. Philosopher Thomas Nagel identified several types of moral luck: resultant luck, circumstantial luck, constitutive luck, and causal luck. Together, they suggest that almost everything about our moral situation is affected by factors beyond our control. The paradox forces us to question whether moral responsibility is coherent. If luck pervades everything and we can't be responsible for luck, can we be responsible for anything? Or must we accept that moral judgment inherently includes response to outcomes, not just intentions? Some philosophers argue we should eliminate outcome from moral judgment entirely, judge only the decision, not the result. Others say outcomes do matter morally, even when random. Still others suggest this reveals deep problems with our concepts of control and responsibility.
You're watching a movie you've seen 3 times before. You know exactly what happens. The hero is hiding in a closet. The villain is searching the house, getting closer. You've watched this scene before. You know the hero escapes. You know exactly how. Yet your heart races. You feel suspense. You're tense. Even though you know the outcome, you're experiencing genuine suspense. How is this possible? Suspense seems to require uncertainty about outcomes. You feel suspense when you don't know what will happen next, when multiple outcomes seem possible. The emotion depends on not knowing. But when you re-watch a movie, you do know. You have certain knowledge of how it ends. There's no uncertainty whatsoever. Yet you feel suspense anyway. This is the paradox of suspense. We experience suspense even when we have complete knowledge of outcomes. The emotion persists despite certainty. It's not just movies. You reread a thriller novel. You know who the murderer is, yet you still feel tension during the investigation. You watch a historical drama about the Titanic. Everyone knows the ship sinks, yet you feel suspense as the iceberg approaches. Some philosophers argue that we temporarily forget the outcome while experiencing the story. We bracket our knowledge and experience it as if uncertain. But this seems wrong. You simultaneously know and feel suspense. You're aware you know the ending. Others suggest suspense isn't really about uncertainty about outcomes. It's about something else. The character's uncertainty, or uncertainty about how the outcome will unfold even if we know what happens, or the experience of imaginatively placing ourselves in the uncertain position of the characters. Still others argue that suspense is a more primitive emotional response that doesn't actually require uncertainty. It's triggered by signs of danger or tension, regardless of our cognitive knowledge about outcomes. The paradox of suspense reveals that emotions are more complex than we think. They don't simply follow from our beliefs. We can feel fear while knowing we're safe. We can feel suspense while knowing the outcome. Our emotional system and our belief system operate somewhat independently. This has implications for understanding art, entertainment, and emotional experience generally. Why do we enjoy being scared or tense when watching fiction? The paradox suggests emotions can be engaged by imagination even when knowledge contradicts them.
Level 37. The paradox of friendship. True friendship is characterized by genuine care for another person for their own sake. You want what's best for your friend because you value them as a person, not because of what they do for you. Aristotle called this virtuous friendship. Friendship based on mutual appreciation of each other's character, not utility or pleasure. It's the highest form of friendship. But here's a question. What if your friend benefits you? What if the friendship makes you happier, less lonely, more fulfilled? Does that mean your friendship isn't genuine? Of course not. Friendships do benefit us. Good friends make our lives better. That doesn't make the friendship false. But now think harder. Suppose you care about your friend genuinely, for their own sake. You want them to be happy. When they succeed, you feel joy. When they suffer, you feel pain. But their happiness makes you happy. Their well-being serves your interests. By caring about them, you've made their welfare part of your welfare. Their flourishing benefits you directly. So are you really caring about them for their own sake, or are you caring about them because their well-being has become part of your well-being? Are you ultimately serving your own interests? This is the paradox of friendship. Genuine friendship requires caring for another for their own sake, not for benefit to yourself. But caring about another for their own sake creates benefit to yourself.
So the benefit you receive undermines the claim that you're acting without self-interest. The paradox connects to ancient debates about altruism and egoism. Psychological egoists argue all actions are ultimately self-interested. Even apparent altruism serves the agent's interests. You help others because it makes you feel good. But is it really egoism if you've transformed your interests to include others? If your friend's happiness genuinely matters to you, then caring about them isn't serving some separate self-interest, they're part of yourself. The paradox of friendship reveals that the boundary between self and other isn't as clear as we assume. Deep relationships change what counts as your interests. When you truly love or befriend someone, the distinction between for their sake and for your sake breaks down. Some philosophers embrace this. They argue genuine friendship dissolves the self-other distinction. You share interests with friends. Others maintain we can distinguish different types of interests. You can care about your friend for their sake, even though this caring benefits you. The paradox of friendship shows that human connection is more complex than simple self-interest or pure altruism. Love and friendship create a shared space where your good and my good become intertwined.
Level 38. The Paradox of Thrift. The economy enters a recession. People become worried about their financial future. They decide to be responsible and prudent. They start saving more money and spending less. Each individual is acting rationally, protecting themselves against uncertainty. Individually, this makes perfect sense. Saving is wise. Financial caution is rational. Each person is doing the right thing for their own situation. But when everyone saves and stops spending, businesses see demand drop. With lower demand, companies cut production. They lay off workers. Unemployment rises. Income falls. The economy shrinks further. Now, people are even more anxious. They try to save even more. They cut spending further. This creates more layoffs, less income, deeper recession. The economy spirals downward. The paradox, what's rational and beneficial for each individual becomes harmful for everyone collectively. Individual prudence creates collective disaster. If everyone had kept spending, the economy would have remained healthy and everyone would be better off. This is the paradox of thrift, articulated by economist John Maynard Keynes. It reveals a fundamental tension between individual rationality and collective outcomes. The paradox is an example of the fallacy of composition. What's true for the part isn't true for the whole. Saving is good for one person, but saving is not good for everyone simultaneously. During the Great Depression, this paradox was tragically real. Everyone tried to save. Everyone cut spending. This collective caution made the depression worse. The individual rational behavior deepened the collective suffering. The paradox has policy implications. During recessions, governments often try to increase spending to compensate for reduced private spending. They run deficits, invest in infrastructure, try to maintain demand. This seems to contradict common sense. You should tighten your belt during hard times, not spend more. But Keynesian economics argues that what's true for households isn't true for nations. When private actors save, government should spend. When everyone tries to save simultaneously, someone needs to maintain demand or the economy collapses. Critics argue this is too simple, that it ignores long-term effects and the importance of saving for investment. But the paradox reveals an important truth. Individual rationality doesn't automatically aggregate to collective rationality.
Sometimes everyone doing the right thing for themselves creates the wrong outcome for everyone. The paradox of thrift shows that economics is counterintuitive. It shows that individual and collective logic can diverge. It demonstrates why economic policy can't simply scale up from individual household decisions.
In formal logic, we use a conditional statement. If A, then B. This is written as A implies B. It's one of the most basic logical structures. But in formal logic, this conditional has a strange property. If A, then B is considered true whenever A is false, regardless of whether B is true or false. Let's see what this means with concrete examples. If the moon is made of cheese, then Paris is the capital of France. The moon is not made of cheese. A is false. According to formal logic, this conditional statement is true. It's a true statement that if the moon were made of cheese, then Paris would be the capital of France. But that seems absurd. The moon's composition has nothing to do with French geography. There's no connection between these facts, yet logic calls this statement true. Here's another. If the moon is made of cheese, then Paris is not the capital of France. The moon still isn't cheese. A is still false. So this statement is also true by the same logic. Both statements are true. If moon cheese, then Paris is capital, and if moon cheese, then Paris is not capital. Two contradictory consequences, both supposedly true conditionals. This is the paradox of material implication. In formal logic, any conditional with a false antecedent is true. Any conditional with a true consequent is true. This means if pigs fly, then 2 + 2 = 4 is true. If pigs fly, then 2 + 2 = 5 is also true. This seems to make the conditional meaningless. True conditionals seem to require some connection between antecedent and consequent. If you heat ice, it melts is true because there's a causal relationship. If you heat ice, then Jupiter is large might have a true antecedent and true consequent, but it's not a meaningful conditional. There's no connection. Yet formal logic treats all these as equally valid true conditionals. Logicians have developed alternative systems, relevant logic, connexive logic, that try to capture our intuition that conditionals require relevance between parts. But material implication remains standard in classical logic. The paradox reveals that formal logic and natural language don't align perfectly. True logic and meaningful truth come apart. What satisfies formal definitions might violate intuitive understanding. This matters for mathematics, computer science, and philosophy. When we formalize reasoning, we might lose important features of how we actually think. The paradox of material implication reminds us that logic is a tool, not a perfect mirror of human reasoning.
Level 40. The paradox of self-amendment. A constitution contains rules for how the government operates. It also contains rules for how to amend the Constitution itself. You can change the Constitution, but you must follow the amendment procedure specified in the Constitution. Now, imagine a Constitution that says, "This Constitution can never be amended." Can such a rule be changed? If the rule can be changed, then the Constitution can be amended. But the rule says it cannot be amended, so changing the rule violates the rule. You can't legally change the rule that says you can't change rules. But if the rule cannot be changed, then the Constitution has permanent, unchangeable content. It constrains all future generations forever. No democratic process, no matter how strong the consensus, can alter it. This seems problematic. Should one generation be able to bind all future generations absolutely?
Should the founding document be completely immune to change, even by overwhelming democratic will? But now imagine the opposite. A constitution that says this constitution can be amended by any procedure at all, including changing this amendment rule. This seems maximally flexible. Any amendment process is allowed, but this means you could amend the Constitution to make it unamendable. You could use the flexibility to eliminate flexibility. The openness enables its own closure. This is the paradox of self-amendment. Constitutional rules that govern their own change create logical loops. Can a fundamental law determine whether it can be changed? Can an amendment rule apply to itself? Real constitutions face this. The U.S. Constitution can be amended, but can you amend the amendment process itself? Could you make the Constitution unamendable? Different legal scholars give different answers. Some argue there are implicit limits. Certain foundational features are beyond amendment even if the text doesn't explicitly protect them. Others argue that no generation can bind future generations. If enough people agree, anything can be changed. The paradox reveals deep questions about law and authority. Where does a constitution's authority come from? If from the people, can the people unmake what they made? If from itself, can it limit itself absolutely? This connects to philosophy of law and political theory. How can law regulate its own creation and destruction? How can rules determine when rules can be changed? The paradox of self-amendment shows that legal systems contain self-referential structures that resist neat logical resolution.
Level 41. The Paradox of Tristram Shandy. Tristram Shandy is writing his autobiography. He's extremely detailed and thorough. So thorough that it takes him 1 full year to write about just 1 day of his life. On January 1st, he begins writing about the first day of his life, his birth. It takes him the entire year to complete that single day's account. By December 31st, he's finished writing about day 1. On the next January 1st, he begins writing about the second day of his life. Again, it takes him a full year. By the end of that year, he's written about 2 days total. This continues. Each year, he writes about 1 more day. Year 3 covers day 3. Year 4 covers day 4. The problem is obvious. He's falling behind. His life keeps adding days faster than he can write about them. He's living 365 days per year, but only writing about 1 day per year. He can never catch up. He'll never finish his autobiography. But now, the philosopher Bertrand Russell pointed out something strange. Suppose Tristram Shandy could live forever. Suppose he's immortal and continues this process infinitely. Given infinite time, Tristram will eventually write about every day of his life. Day 1 gets written in year 1. Day 2 gets written in year 2. Day 100 gets written in year 100. Day 1,000,000 gets written in year 1,000,000. Every day, no matter how far in the future, has a corresponding year when it will be written. There's a 1-to-1 correspondence between days lived and years of writing. Therefore, mathematically, he will complete his autobiography. Every day will eventually be recorded.
But he's always falling behind. At any finite point in time, he's written about far fewer days than he's lived. The gap keeps growing. Yet, given infinity, there's no day that won't eventually be written. This is the paradox of Tristram Shandy. It reveals counterintuitive properties of infinity. A process that's perpetually falling behind can still, given infinite time, be complete. An infinite task can have all its steps accomplished, even though at every finite stage it appears hopelessly incomplete. The paradox shows that infinity doesn't behave like large finite numbers. Intuitions that work for finite quantities fail for infinite ones. You can have infinite days and infinite years and match them perfectly, one to one, even though days accumulate faster than years. This connects to deeper questions in mathematics about infinite sets and cardinality. It relates to Hilbert's hotel, where an infinite hotel that's completely full can still accommodate infinite new guests. The Tristram Shandy paradox demonstrates that completing infinite tasks isn't logically impossible, it's just impossible in finite time. Consider this principle. All truths are knowable. If something is true, then it's possible for someone to know it. This seems reasonable. Truth shouldn't be permanently beyond human reach. Now consider a specific truth. No one knows that it's raining. Suppose it actually is raining, and no one currently knows this fact. Then, no one knows that it's raining is true. It's a true statement about the current state of knowledge. According to our principle, this truth must be knowable. Someone could, in principle, know that no one knows it's raining. But think about what happens if someone knows this. If Sarah knows that no one knows it's raining, then Sarah knows it's raining. But if Sarah knows it's raining, then it's false that no one knows it's raining. Someone does. Sarah does. So the moment the statement, "no one knows it's raining," becomes known, it becomes false. The act of knowing it makes it untrue. The statement cannot be known while remaining true. This is the paradox of knowability, also called Fitch's paradox, after the logician who formalized it. It shows that the innocent-seeming principle, all truths are knowable, leads to contradiction. The paradox has a general form. Take any unknown truth, any fact that's true but no one currently knows it. Call this statement P. Now form the conjunction, P is true and no one knows P. This conjunction is true. P is true and no one knows it. But it cannot be known, because knowing it would make the second part false. So here's a truth that cannot be known. Therefore, either some truths are unknowable or there are no unknown truths. If all truths are knowable, then there are no unknown truths. Everything true is already known. But obviously there are unknown truths. We discover new facts constantly. The paradox of knowability challenges verificationism, the philosophical view that truth and knowability are intimately connected. It shows that allowing unknown truths while maintaining that all truths are knowable creates logical problems. Some philosophers respond by distinguishing actual knowledge from possible knowledge in more sophisticated ways. Others accept that some truths are indeed unknowable. Still others argue the paradox reveals problems with how we formalize knowledge in logic. The paradox of knowability shows that even simple epistemological principles can have surprising logical consequences when carefully analyzed.
You want to run across a racetrack. To cross the entire track, you must first cross half of it. That makes sense. But before you can cross half the track, you must first cross a quarter of it. And before crossing a quarter, you must cross an eighth. Before an eighth, a 16th. This division continues infinitely. Before you can cross any distance, you must first cross half that distance. And before that half, you must cross half of the half. On, infinitely. So before you can move at all, you must complete an infinite number of tasks.
You must cross the first half of the first half of the first half, infinitely many subdivisions. There's no first step. Any movement requires completing infinite prior movements. Therefore, Zeno argued, you can never start moving. You can never even take the first step because there is no first step. Between you and any point ahead lie infinite points you must reach first. This is Zeno's racetrack paradox, also called the dichotomy paradox. Like his other paradoxes, it challenges our understanding of motion and infinity. We know people do cross racetracks. Motion happens. So where does the reasoning fail? The ancient response was that you cannot actually complete infinite tasks, but modern mathematics, through calculus, showed that infinite series can sum to finite values. The infinite subdivisions of distance sum to the total distance. The infinite subdivisions of time sum to finite time. Half the distance takes half the time. A quarter takes a quarter time. An eighth takes an eighth time. The infinite series 1/2 plus 1/4 plus 1/8 and so on equals exactly 1. The infinite steps take finite total time. But Zeno's challenge remains provocative. Can you actually complete infinite tasks? Or does calculus just describe the limit of the process without explaining how infinite steps are accomplished? Modern physics adds another layer. If space and time are quantized, made of discrete smallest units, then there aren't actually infinite subdivisions. You'd reach a smallest possible distance and time. But if space and time are continuous, the paradox stands. The racetrack paradox shows that infinity and continuity create conceptual problems even for simple everyday actions. Motion, the most obvious physical phenomenon, becomes philosophically puzzling when examined carefully. What seems impossible happens constantly.
You prefer coffee to tea. You prefer tea to hot chocolate. So naturally, you prefer coffee to hot chocolate. This is transitive preference. If you prefer A to B and B to C, you prefer A to C. This seems like basic rationality. But now consider a different scenario. You're choosing between 3 vacation options. Option A, beach vacation, great weather, poor food, moderate activities. Option B, mountain vacation, moderate weather, great food, poor activities. Option C, city vacation, poor weather, moderate food, great activities. You compare A and B. Beach has better weather, both have one great and one poor feature. You prefer A to B. You compare B and C. Mountain has better food, both have one great and one poor feature. You prefer B to C. So you should prefer A to C, right? Beach to city? But when you compare A and C directly, city has better activities. Both have one great and one poor feature. You prefer C to A. Now you have circular preferences. You prefer A to B, B to C, and C to A. You're going in a circle. This is intransitive preference. This seems irrational, but it can happen when options differ along multiple dimensions, and you weight those dimensions situationally based on the specific comparison you're making. This is the paradox of intransitive preferences. It shows that rational-seeming pairwise comparisons can create irrational overall preferences. The paradox has practical consequences. Imagine someone with these preferences betting on their choices. They'd accept a trade from B to A, paying a small fee, then trade from C to B, paying again, then C to A, paying again. Now they're back where they started, but poorer. They've been money pumped, exploited through their own preferences. Economists and decision theorists argue that rational agents must have transitive preferences to avoid being exploited. But psychological research shows humans often have intransitive preferences in practice. We're not perfectly rational. The paradox connects to voting theory. When groups vote on multiple options, majority preferences can be circular. Most people prefer A to B and B to C, but also prefer C to A. This is Condorcet's paradox, and it shows that collective preferences can be circular even when individual preferences are rational. The paradox of intransitive preferences reveals that rationality is more complex than it appears. Simple pairwise rationality doesn't guarantee overall coherent preferences.
Human decision-making involves trade-offs and context sensitivity that can create these cycles.
Leibniz's law states if two things are identical, they share all the same properties. This is called the indiscernibility of identicals. If A equals B, then anything true of A is true of B. This seems obviously correct. If Clark Kent is Superman, then anything true of Clark Kent is true of Superman. They're the same person. But now consider this. Lois Lane believes Clark Kent is a reporter. That's true. Lois believes this. But Lois does not believe Clark Kent is Superman. In fact, she explicitly believes Clark Kent is not Superman. So here's the problem. Clark Kent has the property believed by Lois to be a reporter. Superman does not have the property believed by Lois to be a reporter. She doesn't believe Superman is a reporter. She knows he's a superhero. Clark Kent and Superman differ in their properties. One is believed to be a reporter, the other isn't. By Leibniz's law, they can't be identical, yet they are the same person. This is a version of the paradox of identity. It challenges Leibniz's law when applied to beliefs, desires, and other intentional attitudes. The paradox appears in many forms. The morning star and the evening star are both the planet Venus, but ancient people believed the morning star appeared in morning and did not believe the evening star appeared in morning. They thought they were different objects. Same thing, different beliefs about it. Philosophers have proposed solutions. Some argue that Leibniz's law only applies to real properties, not to how things are thought about. The property believed by Lois to be a reporter isn't really a property of Clark. It's a property of Lois's mental state. Others distinguish between meaning and reference. Clark Kent and Superman refer to the same person, but mean different things. Lois believes something about the meaning, not the reference. Still, others argue this shows that identity is more complex when involving intentional contexts, beliefs, knowledge, desires. What's true in these contexts doesn't follow simple substitution rules. The paradox of identity reveals that reference and meaning can come apart. The same object can be thought about in different ways. Identity isn't always transparent. You can be related to the same thing under different descriptions without realizing it. This has implications for philosophy of mind, philosophy of language, and even artificial intelligence. How do we represent beliefs about things? How do identity and difference work in mental states? The paradox shows these are subtle questions. Level 46, the paradox of the surprise party. Your friends are planning a surprise party for your birthday. They tell you, "We're throwing you a surprise party this week. It will be on one of the next 7 days. But it will be a surprise. You won't know which day until it happens." You think about this logically. The party cannot be on the 7th day, Saturday, because if you reach Friday night without a party, you'll know it must be Saturday. It wouldn't be a surprise. So Saturday is impossible. Now that Saturday is eliminated, Friday is the last possible day. But if you reach Thursday night without a party, you'll know it must be Friday. No surprise. So Friday is also impossible. Continuing this reasoning, you eliminate Thursday, Wednesday, Tuesday, Monday, and finally Sunday. A surprise party is logically impossible. You relax, confident there will be no party. Wednesday arrives. Your friends throw the party. You are completely surprised. But wait, your logic was perfect. How did you end up surprised when you proved surprise was impossible? This is the surprise party paradox, a variant of the unexpected hanging. The error is subtle and has sparked debate for decades. The key is that your conclusion, "there will be no party," is what enables the surprise. By reasoning that the party is impossible, you stop expecting it. This very lack of expectation makes surprise possible. If you truly believed your reasoning, you'd expect no party. But then a party on any day would surprise you, including Saturday. Your reasoning defeats itself by changing what you expect. The surprise party paradox reveals problems with reasoning about your own future knowledge and expectations. When you conclude, "I cannot be surprised,"
you change your mental state in a way that makes surprise possible again. This connects to self-defeating prophecies and strange loops in epistemology. Some conclusions, when believed, make themselves false. Knowing certain things changes whether those things remain true. The surprise party paradox shows that surprise isn't just about what happens, but about your expectations. And reasoning about your own future expectations can create these paradoxical loops where valid logic leads to false predictions. It's also a reminder that in real life, logic has limits. Your friends don't need to solve the paradox to surprise you. They just need to throw the party. Reality doesn't wait for logical resolution.
Level 47. The paradox of enrichment. An ecosystem has predators and prey living in balance. Wolves eat rabbits. The rabbit population is stable. The wolf population is stable. The system is in equilibrium. An ecologist wants to help the rabbits. More food for rabbits means more rabbits, which seems good. So they enrich the environment. They add more grass and vegetation for the rabbits to eat. What happens next seems like it should be positive. More food means the rabbit population grows. With more rabbits, the wolves have more food, so the wolf population grows too. Everything increases. The ecosystem becomes more abundant. But that's not what happens. The rabbit population does initially increase, but then, with abundant food, the rabbits multiply rapidly. The sudden abundance of rabbits causes the wolf population to explode. The wolves, now numerous, devour rabbits at an unsustainable rate. The rabbit population crashes. With too few rabbits, the wolves starve. The wolf population crashes. Now both populations are at lower levels than before, or one population goes extinct entirely. The enrichment that was meant to help instead destabilizes the system. Adding resources created collapse. More food led to less life. This is the paradox of enrichment, a phenomenon in ecology and systems theory. It shows that making an environment more resource-rich can actually harm the populations living there. The mechanism involves oscillations and instability. In a resource-poor environment, predator and prey populations stay stable because growth is limited. In a resource-rich environment, populations can fluctuate wildly, creating boom-bust cycles that can spiral into extinction. The paradox appears in real ecosystems. Adding fertilizer to lakes can cause algae blooms that ultimately kill fish. Providing abundant food to certain populations can trigger unsustainable growth followed by collapse. It has broader applications. In economics, rapid resource injection can destabilize markets. In organizations, too much sudden growth can lead to collapse. What seems like pure benefit, more resources, can be destabilizing. The paradox of enrichment reveals that complex systems have their own dynamics. Interventions with good intentions can have counterintuitive, harmful effects. More isn't always better. Stability sometimes depends on scarcity. Systems can be harmed by abundance. This is a warning about unintended consequences and the importance of understanding systemic effects before intervening. What helps in isolation can harm in context. The paradox shows that ecology, like many fields, requires thinking in systems, not just parts.
Level 48. The paradox of confirmation. A scientist wants to test the hypothesis, all swans are white. How do they gather evidence? They go out and observe swans. They see a white swan. This confirms the hypothesis. They see another white swan. More confirmation. Each white swan provides evidence that all swans are white. This is straightforward scientific reasoning. But remember the raven paradox we discussed earlier.
The hypothesis, all swans are white, is logically equivalent to all non-white things are non-swans. These statements mean exactly the same thing. So anything that confirms one statement should confirm the other. If seeing a white swan confirms all swans are white, then seeing a non-white non-swan should equally confirm all non-white things are non-swans, which means it confirms all swans are white. Your red car is non-white and non-swan, so your red car confirms that all swans are white. Your blue shoes confirm that all swans are white. Every non-white non-swan in the universe provides evidence about swans. But now consider further. You don't need to look at swans at all. You could confirm all swans are white by examining your room and noting that everything non-white is not a swan. But here's where it gets even stranger. Suppose you're testing all swans are white and you observe a black swan. This clearly disconfirms the hypothesis. You found a counterexample. But all swans are white is equivalent to all non-white things are non-swans. If you see a black swan, you found a non-white thing that is a swan. This disconfirms all non-white things are non-swans. So the black swan disconfirms both the hypothesis and its logical equivalent. That seems fine. They're equivalent, so evidence should affect them the same way. But by the same logic, a white swan should disconfirm all swans are non-white. And all swans are non-white is equivalent to all white things are non-swans. So a white swan disconfirms all white things are non-swans. But that means a white swan is evidence against the claim that white things aren't swans. It's evidence that white things can be swans, which seems to confirm, not disconfirm, the original hypothesis. This is the paradox of confirmation. Logical equivalence and evidential confirmation don't align the way we expect. What confirms one statement might not confirm its logical equivalent in the way that feels intuitively right. The paradox reveals deep problems in philosophy of science about what counts as evidence and how confirmation works. It shows that formalizing scientific reasoning is more complex than simply counting supporting observations.
Level 49. The paradox of deterrence. Two nations are locked in a nuclear standoff. Each possesses weapons that could destroy the other. Each side makes a threat. If you attack us, we will retaliate with nuclear weapons and destroy you completely. This threat creates deterrence. Neither side attacks because the retaliation would be catastrophic. The threats keep the peace. Mutually assured destruction prevents war. But now think carefully about the nature of this threat. Suppose one side actually does attack. They've launched their nuclear weapons. Your nation is destroyed or about to be destroyed. At this point, should you retaliate? Your nation is already destroyed. Launching your weapons won't save it. Retaliation will kill millions of innocent people in the enemy nation and possibly trigger global nuclear winter, ending human civilization. From a rational perspective, retaliation serves no purpose. Your nation is already lost. Revenge won't bring it back. Retaliating only adds to the catastrophe. The rational choice is not to retaliate. But if the other side knows you're rational, they know you won't actually retaliate after being attacked. And if they know you won't retaliate, then the threat is empty. Your deterrence is a bluff. And if deterrence is a bluff, it doesn't prevent attack. For deterrence to work, you must credibly threaten to do something irrational, to retaliate even when retaliation serves no purpose. You must convince the other side you will act against your own rational self-interest. This is the paradox of deterrence. Effective deterrence requires credible threats, but carrying out the threat, if it comes to it, would be irrational. So rational actors cannot make credible deterrence threats, yet deterrence only works if the threats are credible. Game theorists have explored solutions. Maybe you commit to automatic retaliation, a doomsday machine that retaliates regardless of later rational considerations. You remove the decision from human control,
creating credibility through loss of control. Or maybe you cultivate a reputation for irrationality, convince the other side you might retaliate out of spite, anger, or madness, even though it's not rational. Appearing irrational becomes strategic. The paradox reveals deep problems in strategic thinking. Sometimes rationality requires appearing irrational. Credibility sometimes requires surrendering control. The logic of threats and deterrence doesn't align neatly with rational decision-making. This paradox was central to Cold War nuclear strategy and remains relevant today. How do you prevent conflict when prevention depends on threatening actions you shouldn't actually carry out?
You want to be happy, so you pursue happiness directly. You ask yourself throughout the day, am I happy right now? How can I be happier? You make decisions based on maximizing your happiness. You track your mood, analyze what brings you joy, and organize your life around these happiness-producing activities. This seems like the most rational possible approach. If happiness is the goal, pursue it systematically and directly. But psychological research shows this strategy backfires. People who explicitly pursue happiness as their primary goal tend to be less happy than people who pursue other goals. The direct pursuit of happiness tends to make people more anxious, more self-focused, and, ironically, less happy. Meanwhile, people who focus on other things, helping others, mastering skills, creating art, building relationships, pursuing meaning, often report higher happiness. They're not trying to be happy, they're absorbed in something beyond themselves, yet happiness comes to them as a byproduct. Why does this happen? When you focus on your own happiness, you become self-conscious. You're constantly monitoring your emotional state, evaluating whether you're happy enough, comparing your current happiness to some ideal. This self-focused attention prevents the unself-conscious engagement that actually produces joy. True happiness seems to require self-forgetting. You need to lose yourself in an activity, be absorbed in something meaningful, stop asking whether you're happy. The moment you step back to ask, am I happy? You've broken the spell. It's similar to falling asleep. The harder you try to fall asleep, the more awake you become. The effort defeats the goal. Sleep requires letting go of the effort to sleep. Or consider trying to be spontaneous. The moment you try, you're no longer spontaneous. Genuineness requires not trying to be genuine. This is a deeper version of the paradox of hedonism we discussed earlier. It reveals that many of the best things in life cannot be obtained by pursuing them directly. They must come as side effects of pursuing something else. Philosophers distinguish between happiness as a goal and happiness as a byproduct. Direct pursuit fails, indirect approach through meaningful engagement succeeds. This has practical implications. Instead of asking, what will make me happy, ask, what's worth doing? Pursue meaning, virtue, connection, mastery. Let happiness emerge naturally from a well-lived life rather than making it an explicit target. The paradox shows that human psychology is not straightforwardly instrumental. We can't simply identify a goal and pursue it directly. Some goals require indirect approaches. Some goods must be pursued obliquely, as byproducts of other pursuits.
We've discussed whether an omnipotent being can create a stone too heavy to lift, but let's explore a deeper version of this paradox. Can an omnipotent being create another being that is also omnipotent? Think about what this means. If God creates another being with unlimited power, then there are now two omnipotent beings. But can there be two beings with unlimited power? Suppose God creates another omnipotent being, call them being X. Now being X, being omnipotent, wants to destroy God. Can being X do this? If being X cannot destroy God, then being X is not truly omnipotent. There's something they cannot do. But can God prevent being X from destroying God? If God cannot prevent this, then God is not omnipotent. But if God can prevent it, then being X is not omnipotent because God can limit what being X does. Either way, we can't have two truly omnipotent beings. Their powers would conflict.
one being's unlimited power would limit the other's power. But if God cannot create another omnipotent being, then there's something God cannot do, create that being. So God is not truly omnipotent. Here's another angle. Can God create a being that God cannot control? If God can create such a being, then God lacks control over something. Contradiction. If God cannot create such a being, then God cannot create it. Also a contradiction. Or consider time. Can God change the past? If God is omnipotent, God should be able to make it so something that happened never happened. But if something happened, then making it not have happened seems logically impossible. It both happened and didn't happen. Some argue omnipotence means the power to do all logically possible things, not logically impossible things. God cannot make square circles because square circle is just a contradiction, not actually a thing. Similarly, a past that both happened and didn't happen is not a thing. But this limits omnipotence. It means there are things God cannot do, all the logically impossible things. Is that truly unlimited power? This advanced paradox of omnipotence shows that the concept of unlimited power contains internal contradictions that cannot be resolved by simple redefinition. Every version of omnipotence seems to encounter situations where true unlimited power becomes logically incoherent. The paradox reveals that some concepts might be too extreme to be coherent. Absolute infinity might strain logic beyond the breaking point. Perhaps ultimate power is one of those concepts that seems meaningful but dissolves under careful analysis.
Level 52. The paradox of nihilism. A nihilist believes that nothing has meaning or value. Life is meaningless, morality is baseless, truth is arbitrary, nothing matters. This is their philosophy, their worldview. But now ask, is that statement itself meaningful? Is the claim, nothing has meaning, a meaningful claim? If nothing has meaning, then the statement, nothing has meaning, has no meaning. It's just sounds, marks on paper, neural firing, signifying nothing. You can't meaningfully claim that nothing is meaningful, because the claim itself would be meaningless. But if the statement, nothing has meaning, is meaningful, if it successfully communicates something true about reality, then at least one thing has meaning. The nihilistic claim itself has meaning, so not everything is meaningless. Either way, nihilism defeats itself. If it's true, it cannot be meaningfully stated. If it can be meaningfully stated, it's false. Here's another angle. The nihilist cares about nihilism. They argue for it, defend it, try to convince others. But why bother if nothing matters? The very act of advocating for nihilism shows that something matters to them. At minimum, nihilism matters. If truly nothing mattered, you wouldn't argue about it. Arguing shows caring. Caring shows mattering. The passionate nihilist contradicts themselves through their passion. Or consider this. The nihilist claims there are no values, but they presumably value truth over falsehood. That's why they want their nihilistic view to be believed rather than rejected. They value intellectual honesty, logical consistency, accurate understanding of reality. These are values. This is the paradox of nihilism. The position that nothing has value or meaning cannot coherently be held or expressed. The very act of asserting nihilism demonstrates that something has value, at minimum, the assertion itself. Some respond by distinguishing types of meaning. Maybe conventional or subjective meaning exists, we create meaning, but objective or ultimate meaning doesn't exist. Nihilism might be about the latter, not the former. Others embrace the paradox, arguing that nihilism is a stance or attitude rather than a belief to be argued for. It's not a claim within the language game, but a rejection of the game itself. Still others accept that full nihilism is incoherent and instead adopt partial skepticism about specific values while accepting that some framework of meaning is unavoidable. The paradox of nihilism shows that some forms of radical skepticism are self-refuting.
You cannot coherently deny all meaning while engaging in meaningful communication. Complete meaninglessness, if true, cannot be known or expressed.
We discussed the Sorites paradox with sand, but let's go deeper into what this reveals about reality itself. Consider a mountain. Everyone agrees Mount Everest is a mountain. Everyone agrees a 10-foot hill in your backyard is not a mountain. But where exactly is the boundary? Is a formation that's 500 feet tall a mountain? 1,000 feet? 1,500? At what precise height does a hill become a mountain? You might say it depends on other factors, not just height, but also prominence, how it rises from surroundings. Fine, but the same problem applies. At what exact degree of prominence does something cross from hill to mountain? Every criterion you add still has vague boundaries. You can make the definition more complex, but you can't eliminate vagueness entirely. The boundary between mountain and non-mountain is genuinely fuzzy. Here's what's strange. This isn't just about our language or our ignorance. It's not that there's a precise boundary that we just don't know. The boundary genuinely doesn't exist as a sharp line. This suggests vagueness is a feature of reality itself, not just our descriptions. The world contains genuinely borderline cases, things that are neither clearly in a category nor clearly out of it, but genuinely in between. But classical logic assumes everything is either true or false. Either this formation is a mountain or it's not. There's no third option. Yet vagueness seems to demand a middle ground. Things that are sort of mountains, partially tall, somewhat bald. Some philosophers developed fuzzy logic, systems where statements can be partially true. This formation is a mountain might be 70% true. This captures vagueness mathematically. Others argue for supervaluationism. There are many ways to make vague terms precise, and a statement is definitely true if it's true on all precipitations, definitely false if false on all, and indeterminate otherwise. Still others bite the bullet and say there are precise boundaries, we just don't and can't know where they are. This is epistemicism. Vagueness is about knowledge, not reality. But here's a deeper question. If vagueness is real, what does that mean for identity and existence? Is there a precise fact about when a fetus becomes a person? When a collection of cells becomes alive? When arrangements of matter become conscious? The Sorites paradox might reveal that reality itself doesn't have sharp boundaries for many categories we care about. The world is genuinely fuzzy in certain ways. This has enormous implications for philosophy, law, ethics, and science.
God knows everything. God knows all future events with perfect certainty. This is divine omniscience, complete, perfect knowledge. Right now, God knows what you will eat for breakfast tomorrow. God knew it yesterday, last year, before you were born. God's knowledge is timeless and certain. Tomorrow morning arrives. You stand before your refrigerator deciding what to eat. You feel like you're making a free choice. You could choose cereal, or toast, or eggs, or nothing. The future seems open. But can you actually choose differently than what God knows you'll choose? If God knows you'll eat cereal, can you choose toast instead? If you could choose toast, then God's knowledge would be wrong. But God's knowledge cannot be wrong. That contradicts omniscience, so you cannot choose toast. Therefore, you must choose cereal. Your choice is predetermined by God's foreknowledge. You cannot do otherwise. But if you cannot do otherwise, is it really a free choice? Free will seems to require that you could have done differently. If you had no alternative possibilities, if only one future was available to you, then you didn't freely choose, you just did what you had to do. But if God knows all future choices, then only one future exists. God's knowledge is of what will actually happen, which means everything else won't happen, which means you couldn't have done anything else. Some respond with the distinction between causation and foreknowledge.
God knowing what you'll choose doesn't cause you to choose it. You freely choose, and God knows what you'll freely choose. Knowledge follows reality. It doesn't create it. But this doesn't resolve the core problem. Even if God's knowledge doesn't cause your choice, it still seems to eliminate alternative possibilities. If God knows with certainty that you'll choose cereal, then you will choose cereal. The future is fixed, even if not caused by the knowledge itself. Others argue God exists outside time, knowing all moments simultaneously, so divine knowledge doesn't involve foreknowledge. It's just knowledge of what you're doing at each moment, which doesn't interfere with freedom. Still others accept that free will and omniscience are incompatible. Either God doesn't know the future with certainty, or humans don't have libertarian free will. Something has to give. The paradox of free will and omniscience forces us to choose between concepts we value. Can we have both complete divine knowledge and human freedom, or must we modify our understanding of one or both?
We discussed the donkey starving between two identical hay piles, but let's make this more sophisticated and troubling. Rational choice theory says you should choose the option with the highest expected value. Compare options, calculate outcomes, choose the best. But what if two options have exactly equal expected value? Not just roughly equal, but precisely mathematically equal. Theory says you should be indifferent. Either choice is equally good, so just pick one arbitrarily. The choice doesn't matter. But wait, if the choice doesn't matter, then you have no reason to pick one over the other. Reasons guide choices. If there's no reason to prefer A to B or B to A, how do you choose? Some say just choose randomly, flip a coin. But why should a rational agent resort to randomness? Randomness isn't rational deliberation, it's abdicating the decision to chance. And here's a deeper problem. What if there are infinite options, all equally good? Not just two hay piles, but infinite piles, or infinite career paths, all precisely equally fulfilling. You can't compare infinite options, you can't flip an infinite-sided coin. How does a rational agent choose from infinite equal options? Here's where it gets truly disturbing. Perhaps most important life decisions involve options with very similar expected value. Multiple good career paths, multiple good potential partners, multiple good places to live. The differences in expected outcome might be negligible or unknowable. If rational choice requires picking the option with highest expected value and multiple options tie for highest, then rationality gives no guidance for the most important decisions. Reason runs out precisely when we need it most. Some philosophers argue this shows that rationality isn't just about maximizing expected value. It includes the capacity to make arbitrary choices when options are equal, to just commit to one path without needing a decisive reason. Others suggest that in practice, there are always tiebreakers, small preferences, random factors, even temporal order can serve as reasonable grounds for choice when options are otherwise equal. Still others argue this reveals that humans aren't purely rational calculating machines. We have non-rational capacities, intuition, spontaneity, will that kick in when pure reason is insufficient. But the troubling implication remains. Rational deliberation cannot guide action in cases of equal options, and since many real choices involve rough equivalence, rationality might be less useful than we thought. The advanced Buridan's ass paradox shows that reason has limits. Not everything can be decided by calculation and comparison. Sometimes you must simply choose without reasons, exercising a capacity beyond rationality itself. Level 56, the paradox of self-reference, Quine's paradox. Consider this sentence.
yields falsehood when preceded by itself in quotes. Yields falsehood when preceded by itself in quotes. Read it carefully. The sentence is saying something about what happens when you take a phrase and precede it by itself in quotes. Let's call the phrase after the quotes Q. Q is yields falsehood when preceded by itself in quotes. Now, what happens when we precede Q by itself in quotes? We get exactly the sentence we started with. The whole sentence is Q preceded by Q in quotes. So the sentence is claiming that this very sentence itself yields falsehood. The sentence is claiming it's false. If the sentence is true, then what it says must be the case. It says it yields falsehood, it's false. So if it's true, it's false. If the sentence is false, then what it says is not the case. It says it yields falsehood. If that's false, then it doesn't yield falsehood, it yields truth, so it's true. This is Quine's paradox, a self-referential paradox that doesn't use the words true or false explicitly, but instead uses the concept of yielding truth or falsehood through a specific grammatical construction. It's closely related to the liar paradox, but constructed more subtly. Quine showed you can create paradoxes without even using obvious self-referential language. The self-reference is hidden in the grammatical structure. The sentence talks about what happens when phrases are preceded by themselves. This creates indirect self-reference. The sentence ends up talking about itself without explicitly saying this sentence. Quine's paradox reveals that self-reference is hard to avoid. Even when you try to eliminate obvious self-referential language, you can smuggle it back in through grammatical construction. Any system that allows quotation and substitution can potentially create these paradoxes. This has implications for computer science and formal logic. Programming languages must be designed to prevent these self-referential loops. Logical systems must restrict what can be said about quotations and substitutions. The paradox shows that language has recursive power that can be turned against itself. The ability to quote and manipulate phrases creates the potential for sentences that wrap around and devour themselves logically. Quine's work influenced computational theory and the study of formal languages. It demonstrated that paradoxes aren't just philosophical curiosities, they're fundamental features of any sufficiently expressive language or system.
An author writes a comprehensive book about World War II. The book contains exactly 1,000 specific factual claims. For each claim, the author has done careful research. She believes each claim is true. That's why she published them. But she's intellectually honest. In the preface, she writes, "Despite my best efforts, this book surely contains some errors. Given human fallibility and the complexity of history, some of my 1,000 claims are probably false." Let's think about what she believes. She believes Claim 1. She believes Claim 2, all the way through Claim 1,000. Each individual claim she believes is true. But she also believes that some claims in the book are false. She believes the conjunction of all 1,000 claims contains falsehoods. She believes all 1,000 claims and some claims are false simultaneously. Now extend this. Which specific claims does she believe are false? She can't point to any particular claim and say that one is false because she believes each one is true. She believes errors exist without believing any specific error exists. This is like believing there's a murderer in the room but not believing any particular person is the murderer, or believing you'll make a mistake today without believing any future action will be a mistake. Philosophers call this higher-order uncertainty. You can be uncertain about your overall reliability while being confident about each particular judgment. You can believe you're fallible in general while trusting your specific beliefs. But this creates tension. How can all your specific beliefs be trustworthy if your overall belief system is untrustworthy? How can the parts be reliable if the whole is not?
Some argue this shows belief isn't closed under conjunction for long conjunctions. You can rationally believe P, Q, R, S individually without believing P and Q and R and S all together when the list is long enough. Others say we should distinguish levels of belief. First-order beliefs are about facts. Second-order beliefs are about your beliefs. They can conflict without irrationality. Still others argue this reveals that rational belief involves probabilities, not certainties. Each claim has high probability of being true, but the probability that all 1,000 are true is low. This reconciles the apparent contradiction. The extended preface paradox shows that knowledge and belief are more complex than simple true-false. Confidence, probability, and levels of belief all matter. Perfect consistency might not be achievable or even desirable for finite, fallible creatures like us.
Level 58. The paradox of rational irrationality. You're voting in an election. You want to be an informed voter, so you should research the candidates, study their policies, understand the issues. This takes time, maybe 20 hours of careful research to become genuinely well-informed. But remember, your individual vote almost certainly won't change the outcome. In a national election, the probability your vote is decisive is roughly 1 in 10 million. So the expected benefit of voting carefully versus voting randomly is extremely small. The chance your informed vote matters is vanishingly tiny. Meanwhile, the cost of becoming informed is 20 hours of your time. From a purely rational cost-benefit perspective, spending 20 hours researching is irrational. The expected return doesn't justify the investment. You should rationally remain ignorant and vote randomly, or not vote at all. But now imagine everyone reasons this way. Everyone stays ignorant because rational ignorance is individually optimal. The election is decided by millions of uninformed voters choosing randomly or based on superficial factors. The result is terrible governance. Leaders are chosen poorly. Bad policies are implemented. Society suffers. Everyone is worse off. Rational individual behavior creates collectively disastrous outcomes. Everyone acting on rational self-interest produces mass irrationality at the collective level. This is the paradox of rational irrationality, identified by economist Brian Kaplan. It extends beyond voting to many domains. Why should you recycle your one plastic bottle? Your individual impact on the environment is unmeasurable. Rational ignorance applies here too. Why learn about complex policy issues? Why educate yourself about science, economics, or history? The personal benefit is small. The paradox shows that rationality at the individual level can mandate irrationality at the collective level. When everyone pursues rational self-interest, everyone becomes rationally ignorant and collective outcomes are irrational. Some argue this shows markets fail for public goods. Private rationality doesn't produce public rationality. We need institutions, norms, or different decision frameworks to escape the trap. Others suggest this reveals that humans aren't purely rational in the economic sense. We vote, recycle, and educate ourselves for reasons beyond narrow self-interest, duty, identity, expression, intrinsic interest. Still others argue that rationality is broader than cost-benefit calculation. Perhaps it's rational to be informed because that's what good citizenship means, even if the instrumental benefits are small. The paradox of rational irrationality shows that individual rationality and collective rationality can diverge sharply. Sometimes being rational makes everyone worse off. Sometimes irrationality, duty, or virtue are more rational than rational calculation itself.
Consider the statement, "This paradox is not interesting." If the statement is true, then this paradox genuinely is not interesting. It's boring, unremarkable, not worth thinking about, just another dull statement. But wait, a paradox that claims itself to be uninteresting while being a paradox is actually quite interesting. The self-referential structure, the way it talks about its own interestingness, makes it philosophically noteworthy. So it is interesting. But if it is interesting, then what it claims is false. It says it's not interesting, but it is. So the statement is false. If the statement is false, then the paradox is interesting. But claiming to be uninteresting while being interesting is what makes it interesting. So the statement's falsity makes it true. We're in a loop again. The paradox is interesting if and only if it's not interesting. But here's a deeper layer. As you think about this paradox, you're probably thinking, this is a silly paradox, not profound like the liar paradox or Newcomb's paradox. It's just playing with the word interesting. So you judge it to be uninteresting, which makes the claim this paradox is not interesting true. But the fact that we can have this meta-level discussion about whether it's interesting or not is itself somewhat interesting, which makes it interesting again. The paradox of interesting paradoxes shows that self-reference can be applied to aesthetic or subjective properties, not just logical ones. Interesting is not a purely logical concept, yet it can create paradoxical structures. It also reveals something about gradations. Some paradoxes are deeply interesting, others are trivial word games. Where does this one fall? The judgment itself becomes part of the paradox. This connects to the broader category of paradoxes about second-order properties, properties of properties. Is the property of being interesting itself interesting? Can a statement about its own boringness be boring? The paradox is also somewhat self-effacing. Unlike the liar paradox, which boldly creates contradiction, this paradox seems embarrassed about itself, apologizing for existing, claiming to be unworthy of attention. Yet here we are, discussing it, thinking about it. The very fact that it's being included in a collection of 67 paradoxes suggests someone found it interesting enough to include. So maybe it is interesting after all. Or maybe not. And there's the paradox.
Consider this sentence. This sentence is not known to be true. Call this sentence K. Now, is sentence K true? Suppose K is true, then what it says is the case. What does it say? It says that K is not known to be true. So if K is true, then K is not known to be true. We have a true sentence that cannot be known. But wait, we just figured out that K is true by reasoning about it. We followed the logic and concluded K must be true. So we know K is true. But if we know K is true, then what K says is false. K says it's not known to be true, but we just said we know it's true. So K is false. If K is false, then what it says is not the case. It says it's not known to be true. If that's false, then K is known to be true. But we just concluded K is false. Can we know a false statement to be true? That doesn't make sense. This is the paradox of the knower, a self-referential paradox involving knowledge rather than just truth. It's more complex than the liar paradox because it involves epistemic notions, knowledge, knowability. The paradox reveals problems with how we formalize knowledge in logic. Adding knows to logical language creates new self-referential possibilities that generate contradictions. Some philosophers respond by restricting what can be known. Maybe you can't know self-referential statements about knowledge, but that seems arbitrary. Why should some truths be unknowable just because of their grammatical structure? Others modify the logic of knowledge itself. Maybe knowledge doesn't behave like truth. Maybe it's not closed under logical implication or doesn't distribute over conditionals in expected ways. Still others embrace paraconsistent logics, where some statements can be both true and false without the whole system exploding into contradiction. The knower paradox is particularly important in computer science and artificial intelligence. When we program systems to reason about their own knowledge states, these self-referential structures can create infinite loops or contradictions.
The paradox shows that knowledge about knowledge is more complex than knowledge about the world. It also connects to Gödel's incompleteness theorems. Gödel used self-referential sentences about provability to show that arithmetic contains true, unprovable statements. The knower paradox is a simpler version of the same self-referential technique. The paradox reveals that knowledge, like truth, has strange properties when it refers to itself. Self-awareness, knowing what you know, creates logical complexity that doesn't exist in simple outward-directed knowing.
You know that you have hands. You can see them, feel them, use them. This is certain knowledge, not mere belief. You also know this logical fact. If you have hands, then you are not a handless brain in a vat being fed sensory illusions by a mad scientist. These two pieces of knowledge seem solid. You know you have hands. You know that having hands implies you're not a brain in a vat. Now, logic says, if you know P, and you know that P implies Q, then you should know Q. This is called epistemic closure. Knowledge is closed under known logical implication. So you should know that you are not a brain in a vat. Your knowledge of your hands, combined with the logical implication, should give you knowledge that you're not in the skeptical scenario. But wait, can you really know you're not a brain in a vat? The whole point of the brain in a vat scenario is that everything would seem exactly the same whether you're real or simulated. All your sensory evidence would be identical. So how can you know you're not in that scenario? You can't. It's the ultimate skeptical challenge. You can't rule it out based on your experience. But if you can't know you're not a brain in a vat, then by working backwards, you can't really know you have hands. Because claiming to know you have hands while admitting you can't rule out being a brain in a vat seems contradictory. This is the paradox of epistemic closure. Either we accept that we know almost nothing because we can't rule out skeptical scenarios, or we reject closure and say that knowledge doesn't travel across logical implications. If we reject closure, then you can know you have hands without knowing you're not a brain in a vat, even though you know the first implies the second. But that seems bizarre. How can logical implication not transfer knowledge? Some philosophers embrace skepticism. We don't really know much. Others reject closure for pragmatic reasons. Everyday knowledge doesn't require ruling out far-fetched alternatives. Still others try to show that we can know we're not in skeptical scenarios through some special argument. The paradox reveals a tension between our intuition that knowledge is common and robust and the logical implications of that knowledge. If knowledge followed logical closure strictly, skepticism wins. If it doesn't, knowledge becomes fragmented and strange. This isn't just abstract philosophy. It affects how we think about justified belief, rational certainty, and what counts as knowing something. The paradox of epistemic closure shows that ordinary knowledge claims carry extraordinary logical baggage. Level 62. The paradox of deontic revenge. You're in a moral dilemma. Two children are drowning. You can save one, but not both. Whichever child you don't save will die. Is it morally wrong to let one child drown? Normally, yes. Letting a child die when you could prevent it is wrong. But in this case, you must let one child drown. You have no choice. You cannot save both. So you have a moral obligation to save a child, but you also have a moral obligation to save the other child. You cannot fulfill both obligations. At least one obligation will be violated no matter what you do. Some philosophers say, ought implies can. You're only obligated to do things you're capable of doing. If you can't save both children, then you're not obligated to save both children. You're only obligated to save one. But which one? Is there a moral obligation to save the child on the left versus the right? Usually we'd say no. They're morally equivalent. You're obligated to save a child, but not specifically this one or that one. This creates a strange obligation.
You must save a child, but you're not obligated to save any particular child. You have an obligation to perform an action of a certain type, but no obligation to perform any specific instance of that type. But normally, obligations are to specific actions. You ought to help someone normally means there's someone you ought to help. But here, you ought to save a child, yet there's no child you specifically ought to save. Now add another layer. Suppose after you save one child, someone criticizes you. You should have saved the other child. Are they right? In one sense, yes, you had an obligation to save that other child. Children shouldn't be allowed to drown when savable. But in another sense, no, you did fulfill your obligation. You saved a child as required. This is the paradox of deontic revenge. Situations where moral obligations conflict in ways that make it impossible to avoid wrongdoing, sometimes called moral tragedy or dirty hands. Some argue these situations show that morality is not a complete system. Sometimes there's no right answer. Whatever you do involves wrong. You must choose which wrong to commit. Others say these reveal the limits of obligation-based ethics. Maybe consequences or virtues matter more than duties when duties conflict irreconcilably. Still others bite the bullet. Yes, you do something wrong by letting one child die, but you're excused because circumstances made wrongdoing unavoidable. You act wrongly but blamelessly. The paradox of deontic revenge shows that moral life can involve genuine tragedy. Not all dilemmas have good solutions. Sometimes every option involves moral loss. This has implications for ethics, law, and how we judge people in impossible situations.
Level 63. The paradox of plurality. 3 candidates run for office: Alice, Bob, and Carol. 100 people vote. Here are the results. Alice gets 35 votes. Bob gets 33 votes. Carol gets 32 votes. Alice wins by plurality. She got more votes than anyone else. She becomes the leader and implements her policies. This seems democratic. But now consider, 65 people, a solid majority, voted against Alice. More than half the voters explicitly chose someone else. Most people didn't want Alice to win. Yet Alice has complete power. She won the election. The 65% who opposed her have no power at all. Their preferred candidates lost. Is this democratic? The majority didn't want this outcome, yet this is the outcome. Here's where it gets stranger. Suppose Bob and Carol have very similar views. They're both progressive, while Alice is conservative. The progressive voters split their vote between Bob and Carol. If they had coordinated and all voted for one progressive candidate, that candidate would have won with 65 votes. But because they divided, the majority's will was defeated by their own diversity. This is the paradox of plurality, closely related to problems in voting theory. Plurality voting, where the person with the most votes wins, can produce winners who are opposed by the majority. It gets worse. Suppose Carol wasn't running, then all her voters would likely vote for Bob, who would win 65 to 35. But Carol's presence in the race changed the winner from Bob to Alice, even though Carol never had a chance of winning herself. Carol is a spoiler candidate. She spoiled Bob's chance without having her own chance. Her presence changed the outcome in favor of someone she's least similar to. This happens in real elections constantly. Third-party candidates are accused of spoiling elections. Strategic voting becomes necessary, voting not for your favorite, but for whoever can beat your least favorite. But then people aren't expressing their true preferences. They're gaming the system. Is that democratic? Various alternative voting systems try to solve this problem. Ranked choice voting, approval voting, Condorcet methods. But Arrow's impossibility theorem
shows that no voting system can satisfy all desirable properties simultaneously. The paradox of plurality reveals deep problems with translating individual preferences into collective decisions. Democracy is harder than it looks. Majority rule sounds simple, but implementing it fairly is mathematically impossible in certain ways. This isn't just about elections. Any group decision-making faces these paradoxes. Committees, organizations, societies all struggle with aggregating preferences fairly.
Level 64, the paradox of self-trust. You trust your own reasoning abilities. You believe that when you think carefully and follow logic, you usually reach correct conclusions. This self-trust is fundamental. Without it, you couldn't function or learn. But you also know you're fallible. You've been wrong before. You've made errors in reasoning, believed false things, been overconfident. History is full of intelligent people who were completely wrong about important matters. So you know you make mistakes. You know your reasoning is imperfect, but you're using that very imperfect reasoning to judge that your reasoning is imperfect. How do you know your judgment about your own fallibility is correct? You're using your reasoning to evaluate your reasoning. If your reasoning is unreliable, then your conclusion that your reasoning is unreliable might be unreliable too. Maybe you're more reliable than you think, or maybe you're even less reliable than you think. But either way, you're trying to assess your own reliability using the very faculty whose reliability is in question. This is like trying to test if your ruler is accurate by measuring it with itself. The ruler measures itself as exactly 12 inches, but that doesn't tell you if it's actually accurate. Here's the paradox in sharper form. Suppose you conclude through careful reasoning, I am unreliable at reasoning. If this conclusion is correct, then you've just reasoned correctly about your unreliability. But if you reasoned correctly, you're reliable at reasoning, which contradicts what you concluded. If the conclusion is wrong, then you are reliable at reasoning, but you reached a wrong conclusion, which shows you're unreliable. Some philosophers respond by distinguishing levels. You can trust your reasoning in general while acknowledging specific mistakes, or you can trust local reasoning processes while being uncertain about global reliability. Others argue that self-trust is unavoidable. We have no choice but to trust our own reasoning because that's the only tool we have. Skepticism about our own faculties is self-defeating because it relies on those very faculties. Still others embrace a kind of epistemic modesty. We do our best with imperfect tools, acknowledging circularity but having no alternative. We bootstrap our way to knowledge using imperfect self-reference. The paradox of self-trust reveals that all knowledge rests on trusting faculties we cannot independently verify. Rationality requires a kind of faith in itself. We cannot step outside our own minds to check if our minds are working properly. This has implications for epistemology, cognitive science, and philosophy of mind. How do we justify trusting our own reasoning? The paradox suggests we can't fully, but we must anyway.
We discussed the basic paradox of tolerance. A tolerant society cannot tolerate intolerance, or tolerance self-destructs. But there's a deeper, more troubling version. Who decides what counts as intolerance that must not be tolerated? Where exactly is the line between legitimate disagreement and dangerous intolerance? Suppose a society decides we will not tolerate views that advocate intolerance. But now someone must interpret what advocate intolerance means. Someone must judge which views cross the line. One person thinks traditional religious views about marriage are intolerant. Another thinks criticizing religion is intolerant. Who's right? Both are invoking the principle that intolerance should not be tolerated, but applying it to different targets. The person making this judgment has power. They become the arbiter of what's acceptable. They decide which views are allowed in public discourse and which must be suppressed. But giving anyone this power creates a new form of intolerance, intolerance of ambiguity, complexity, and dissent about where boundaries lie. Here's the paradox. To maintain tolerance, you must be intolerant of intolerance. But identifying intolerance requires making judgments that others may dispute. Enforcing these judgments means being intolerant of those who disagree about what counts as intolerance. So, the tolerant society becomes intolerant not only of intolerance, but of disagreement about intolerance. The exception swallows the rule. The boundary-drawing mechanism becomes a tool of intolerance itself. Moreover, people rarely see their own views as intolerant. Everyone thinks they're defending tolerance against intolerance. The racist thinks tolerance means respecting traditional hierarchies. The anti-racist thinks tolerance means actively dismantling those hierarchies. Both accuse the other of intolerance. This creates perpetual conflict over defining the terms. Who watches the watchers? Who decides who decides? The paradox of tolerance extends infinitely up the chain of meta-judgments. Some argue this shows we need procedural rather than substantive principles, focus on fair processes for debate rather than banning content. Others say some boundaries are clear even if others are debatable. Still others accept that tension is unavoidable and must be negotiated constantly. The advanced paradox of tolerance reveals that protecting freedom requires limiting freedom in ways that are themselves contested. There's no neutral, uncontroversial way to police the boundaries of acceptable discourse. Every solution creates new problems of power and interpretation.
This is the 66th paradox in our collection. There's one more coming, level 67. But consider this statement. This is not the final paradox. If this is not the final paradox, then the statement is true. There's at least one more paradox after this one, which there is. 67 is coming. But think about what happens at level 67. Level 67 will be the final paradox. At that point, if level 66 claimed this is not the final paradox, that statement will still be true. 66 was not final. 67 was. Now suppose this statement said instead, this is the final paradox. If we're at 66 and there's still 67 to come, then the statement is false. This is not the final paradox. But wait, by claiming to be the final paradox at level 66, it draws attention to itself in a way that might make it memorable. Maybe it becomes conceptually final, even if not numerically final. Or maybe claiming finality when there's more to come is itself the paradox. Here's the deeper issue. What makes something final? Is it the last in numerical order? Or is it the most important, the culminating point? Can something be final without being last? And what about paradoxes themselves? Can the set of all paradoxes be final? Or can you always construct one more paradox? Maybe there are infinitely many paradoxes, in which case no paradox can be final. But if paradoxes are infinite, then any claim to finality is false. Yet claiming false finality might itself be a paradox, which would make the claim self-referential and strange in typical paradoxical fashion. This paradox plays with endings, completion, and self-reference in collections. It's aware of its own position in a sequence. It talks about finality while not being final. It points forward to something beyond itself while claiming to be complete. The paradox of the final paradox reveals that endings are harder to define than they appear. When something is truly final, it cannot point beyond itself. But by pointing to what comes after, it proves it's not final. The self-awareness of position in sequence creates paradoxical self-reference. This applies beyond paradoxes. The last book in a series that sets up a sequel, the final episode that leaves things unresolved, the ultimate answer that generates more questions. Finality is slippery, especially when the thing claiming finality knows about its own position. So, is this the final paradox? In one sense, no. 67 follows. In another sense, maybe.
It's the paradox about finality itself, which might make it conceptually ultimate, even if numerically penultimate. But claiming that status might disqualify it. And there's the paradox.
Level 67. The paradox of this collection. You've now encountered 67 paradoxes. This collection claims to present the most logical, mind-bending paradoxes. But consider, is this collection itself paradoxical? The collection includes paradoxes about collections. Russell's barber paradox concerns the set of all men who don't shave themselves. That's about a collection that references itself. We've seen multiple paradoxes that arise from self-reference and self-inclusion. So ask this question: does the collection of paradoxes include itself? Is the collection of all paradoxes itself a paradox? If the collection is not a paradox, then it's incomplete. There exists at least one paradox, itself, that's not included. But we claimed this was a collection of paradoxes. If it's incomplete, it fails its own purpose. If the collection is a paradox, then it includes itself. But a collection that includes itself as a member creates strange loops. The collection is both container and contained. It's simultaneously the whole and a part of the whole. Moreover, we've discussed several paradoxes that involve talking about collections of things where self-inclusion creates problems. This collection of paradoxes is talking about paradoxes, including paradoxes about collections that talk about themselves. The meta-levels multiply. Here's another angle. This collection promises mind-bending logical paradoxes, but is the promise itself paradoxical? Can a collection that causes confusion be clearly understood? If you understand all 67 paradoxes, have they successfully bent your mind, or have you merely organized confusion? The collection claims to be logical, but paradoxes are, by definition, challenges to logic. A logical collection of illogical things is itself a contradictory concept. How can illogic be logically organized? And what about completeness? Have we listed all paradoxes? Obviously not. Philosophers and mathematicians continue discovering new ones, so this collection is incomplete. But it claims to present the most important ones. Who decides what's important? The creator of the collection. But that's subjective judgment, not logical necessity. So the collection might contain paradoxes, but not be a paradox itself. Or it might be a paradox precisely because it attempts to contain paradoxes. Or maybe the question itself is ill-formed. Categories like paradox and collection don't interact in ways that make self-reference coherent. The paradox of this collection is that any attempt to comprehensively organize paradoxes faces the same self-referential problems that create paradoxes in the first place. You cannot stand completely outside paradox to catalog paradoxes. The catalog becomes entangled in what it catalogs. This is perhaps the ultimate paradox. The attempt to understand paradox is itself paradoxical. Every explanation of paradox uses the same logical and linguistic tools that create paradoxes. We cannot escape the structures that trap us. And yet, here we are at the end. Or are we? Is this truly the final word on paradoxes? Of course not. There will always be one more paradox, one more twist of logic, one more way that thought turns back on itself and creates impossible loops. The journey through paradoxes doesn't end, it circles back. And maybe that's fitting. Maybe the most appropriate ending for a collection of paradoxes is no ending at all, just a return to the beginning, an eternal loop, a journey that completes itself by never completing. Welcome to the paradox. You've been here all along.